A war has been raging for billions of years, killing trillions every single day, while we don't even notice. The war is fought by the single deadliest entity on our planet, the bacteriophage, or phage for short. A phage is a virus, not quite alive, not quite dead. Also, they look as if someone made them up. Their head is an icosahedron, a sort of dice with 20 faces and 30 edges. It contains the genetic material of the virus and often sits on a long tail that has leg-like fibers. There are more phages on Earth than every other organism combined, including bacteria. And they are probably everywhere living things exist. Billions are on your hands, in your intestines, and your eyelids right now. Which might make you nervous since phages are responsible for the majority of deaths on Earth. But you're lucky. While they do commit genocide for breakfast, they only kill bacteria. Up to 40% of all bacteria in the oceans are killed by them every single day. But phages also have major flaws. Like any other virus, phages need a host to survive and reproduce. They're not much more than genetic material in a hull, and they specialize. Usually, a phage has chosen one specific bacteria and maybe some of its very close relatives. These are its prey. Imagine a phage as like a cruise missile that only hunts and kills members of one very unlucky family. When a phage finds its victim, it connects its tail fibers with receptors and uses a sort of syringe to puncture the surface. In a weird motion, the phage squeezes its tail and injects its genetic information. Within minutes, the bacteria is taken over. It's now forced to manufacture all the parts of new phages. They only stop when the bacteria is filled up with brand new phages. In the final step, they produce endolysin, a powerful enzyme that punches a hole in the bacteria. The pressure is so high that the bacteria sort of vomits out all of its insides and dies. New phages are released and begin the cycle anew. In the last few years, bacteriophages have enjoyed the attention of the second deadliest beings on Earth, humans. Recently, we've started looking into injecting millions of them into our bodies because we're sort of getting desperate. We screwed up. In the past, a single cut or a sip from the wrong puddle could kill you. Bacteria were our phages, tiny monsters that hunted us mercilessly. But then, about 100 years ago, we found a solution in nature. By accident, we found fungi that produced a compound that killed bacteria, antibiotics. Suddenly, we had a powerful superweapon. Antibiotics were so effective that we stopped thinking of bacteria as monsters. Only the old and weakest among us were killed by them. We used antibiotics more and more for less and less serious causes. We lost respect for the monsters and the weapon. But bacteria are living things that evolve, and one by one, they started to become immune against our weapons. This continued until we had created what are called superbugs, bacteria immune to almost everything we have. This immunity is spreading across the world as we speak. By 2050, superbugs could kill more humans a year than cancer. The days when a cut or bladder infection or a cough could kill you or your loved ones are coming back. In the US alone, more than 23,000 people die from resistant bacteria each year. But it turns out that phages, our tiny killer virus robots, could save us. We can inject them into our bodies to help cure infections. Hold on, how can injecting millions of viruses into an infection be a good idea? Phages are very, very specialized killers of bacteria. So specialized, in fact, that humans are completely immune to them. We are too different. We encounter billions of phages every day, and we just politely ignore each other. Antibiotics are like carpet bombing, killing everything, even the good bacteria in our intestines that we don't want to harm. Phages are like guided missiles that only attack what they're supposed to. Wait a minute, if we use phages to kill bacteria, won't bacteria develop ways of defending themselves? Well, it's more complex than that. Phages evolve too. There has been an arms race between them and bacteria for billions of years, and so far they're doing great. This makes phages smart weapons that are constantly getting better at killing. But even if bacteria were to become immune against our phage, we still might be able to win. It turns out that in order to become resistant to even just a few species of phages, bacteria have to give up their resistance to antibiotics. We might be able to trap them in a catch-22. This has already been successfully tested with a patient who had no other hope left. The bacteria Pseudomonas aeruginosa, one of the most feared bacteria, infected the man's chest cavity. They are naturally resistant to most antibiotics and can even survive in alcoholic hand gel. After years of suffering, a few thousand phages were directly inserted into his chest cavity together with antibiotics the bacteria were immune to. After a few weeks, the infections had completely disappeared. Unfortunately, this treatment is still experimental, and pharma companies are still reluctant to invest the necessary billions in a treatment that has no official approval yet. But things are finally changing. In 2016, the largest phage clinical trial to date began, and phages are getting more and more attention. And we better get used to it, because the era in which antibiotics have been our superweapon is drawing to a close. It might be a weird concept, but injecting the deadliest being on planet Earth directly into our bodies could save millions of lives. Human society is extremely complex and fragile, built upon various pillars. One of them is the honeybee. 1 out of 3 meals eaten by humans is made possible by honeybees. They are so important that if all the honeybees were to die out, thousands of plants would follow, which could lead to millions of people starving in the following years. On top of that, honeybees have a huge economic impact. The dollar value of plants pollinated by them each year is around $265 billion. Food we take for granted would just stop existing without them, or there would be a massive decrease in productivity. Food including apples, onions, pumpkins, and also plants used for feeding livestock, and thus extremely important for our milk and meat. Einstein is often quoted as having said, "If honeybees die out, humans will follow a few years later." Actually, he probably didn't say that, but there might be some truth in the statement. It's unsettling, but honeybees have started to disappear. Millions of hives have died in the last few years. Beekeepers all over the world have seen an annual loss of 30 to 90% of their colonies. In the US alone, bees are steadily declining, from 5 million hives in 1988 to 2.5 million today. Since 2006, a phenomenon called colony collapse disorder has affected honeybees in many countries, and we're not entirely sure what's causing it. All we know is that it's pretty serious. Over the last few decades, bees have seen an invasion of very dangerous foes. Parasites straight out of a horror movie, like a Carapace woody. Microscopic mites that infect the trachea, that's the breathing tubes, of bees. Here, they lay their eggs and feed from the fluids of their victims, weakening them considerably and spending their whole life inside the bees. Or Varroa destructor, a fitting name because they can only reproduce in honeybee hives and are one of the bee's greatest enemies. The female mite enters a honeybee brood cell and lays eggs on the bee larva before it's about to pupate and before the hive bees cover the cell with a wax capping. The eggs hatch and the young mites and their mother feed on the developing bee in the safety of the capped cell. The bee is not normally killed at this stage, just weakened, so it still has enough strength to chew its way through the wax capping and release itself from the cell. As it does, it releases the mother mite and her new offspring from the cell, and these are free to spread across the hive, starting the process over again in a cycle of about 10 days. Their numbers grow exponentially, and after a few months, this can lead to the collapse of the entire beehive. Once outside of the cell, adult mites also suck the bodily fluids of bees and weaken them considerably. To make things worse, they also transmit viruses that harm the bees even more and can lead to birth defects like useless wings. But there are other threats too, such as viruses and fungi. Under normal circumstances, these phenomena should be manageable and are not enough to explain the horrendous amount of dying going on in bees. Over recent years, new insecticides have been introduced that are deadly to bees. Neonicotinoids, a chemical family similar to nicotine, was approved in the early 1990s as an alternative to chemicals like DDT. They attack insects by harming their nervous systems. Today, they are the most widely used insecticides in the world. Globally, they saw sales of 1.5 billion euros in 2008, representing 24% of the global market for insecticides. In 2013, neonicotinoids were used in the US on about 95% of corn and canola crops, and also on the vast majority of fruit and vegetables like apples, cherries, peaches, oranges, berries, leafy greens, tomatoes, potatoes, cereal grains, rice, nuts, grapes, and many more. Bees come into contact with the toxin while collecting pollen or via contaminated water, often bringing material into the hive where it can accumulate and slowly kill the whole colony. The toxins harm bees in a variety of horrible ways. In high enough doses, it quickly leads to convulsions, paralysis, and death. But even in small doses, it can be fatal. It may lead to bees forgetting how to navigate the world, so bees fly into the wild, get lost and die alone, separated from their hives. If this happens often enough, a hive can lose its ability to sustain itself. We know that neonicotinoids are harmful to bees and that we urgently need an alternative to it. But there are billions of dollars to be made in delaying this. Studies sponsored by the chemical industry magically appear to prove a much lower toxicity to bees compared to those produced by independent scientists. There are even more factors contributing to the demise of bees, like too much genetic uniformity, crop monocultures, poor nutrition due to overcrowding, stress because of human activities, and other pesticides. Each of those factors on its own is a major problem for bees, but together they probably account for colony collapse disorder. With parasites upping their game in recent decades, the honeybees are now fighting for survival. It would be a catastrophe if they lost this fight. This is a conundrum we have to solve if we want to continue living with a relative abundance and diversity of food. Humanity is deeply interconnected with Earth and the other life forms on it. Even if we pretend that we're not, we have to take better care of our surroundings, if not to preserve the beauty of nature, then at least to ensure our own survival. What would happen if you were to bring a tiny piece of the sun to Earth? Short answer, you'd die. Long answer, it depends which piece of the sun. Like most of the matter in the universe, our sun is neither solid, liquid, or gas, but plasma. Plasma is when stuff is so hot that the nuclei and electrons can separate and flow around freely, which creates a goo-like substance. So you can imagine our sun as an extremely big, spherical ocean of very hot goo. The deeper you go, the denser and weirder the goo becomes. So let's bring 3 samples, each the size of a house, to our lab here on Earth and see what happens. First sample, the chromosphere. The chromosphere is the atmosphere of the Sun, a layer of sparse gas up to 5,000 kilometers deep that's covered in a forest of plasma spikes that can be almost as big as Earth. It's pretty hot here, between 6,000 and 20,000 degrees Celsius, but if we brought a sample of it to Earth, we're not really getting our money's worth. In the area where we take our sample, the chromosphere is over 1 million times less dense than air, so compared to our atmosphere at sea level, it's basically the same as bringing the vacuum of space down to Earth. The moment our sample arrives, it would immediately be crushed by Earth's atmospheric pressure and implode. Air would rush to fill the vacuum and use as much energy as 12 kilograms of TNT in the process. This creates a high-pressure shock wave which shatters glass, ruptures eardrums, and maybe some internal organs. If you're standing too close, it could kill you, so you'd better keep your distance. Let's go deeper. Second sample, the photosphere. Beneath the chromosphere is the glowing surface of the Sun, the photosphere, which produces the light we see. It's covered in a grid of 1 million hotspots called granules, each of them about as big as the United States and over 5,000 degrees Celsius. These granules are the tops of convective columns, churning gas that brings the heat up from the center of the Sun to its surface. In these columns, a few hundred kilometers down, we take our second plasma sample. It has about the same pressure as our atmosphere on Earth. Though still much less dense than air, its heat supports it, so it won't implode. Our sphere now carries twice as much energy, as much as 25 kilograms of TNT, but this time as heat. For a dazzling instant, this plasma would glow with 1,000,000 times the brightness of the sun seen from Earth, instantly lighting fires throughout our lab. But a few milliseconds later, those fires are all that's left. The plasma has cooled to harmless gas floating up from the flaming ruins. What if we go deeper? Third sample, the radiative zone. Here, the plasma is about 2 million degrees Celsius and so dense and tightly packed that it creates a sort of maze for itself. Energy in the form of photons tries to escape but has to wander for hundreds of thousands of years, bouncing endlessly from particle to particle until it eventually finds an exit. Bringing matter from here to our lab is what experts call a very bad idea. As soon as it arrives in our lab, the extreme pressure that holds the plasma tightly together is gone, and the material explodes with the power of a thermonuclear weapon. Our lab, as well as the city around it, will be destroyed in an instant. On the bright side, there won't be any radioactive fallout. With our lab destroyed, we can abandon the illusion that we're trying to do any science today. What if we go much, much deeper? Last sample, the core. Here in the central 1% of the star, we find 1/3 of the Sun's mass. The matter here is compressed by the weight of the entire star above it. In the center of the core, the temperature is 15 million degrees, hot enough to make helium by smashing together hydrogen, powering the Sun by nuclear fusion. In billions of years after the death of the Sun, this core will remain as a white dwarf. If we brought a sample of it to Earth, it would cause a lot of inconvenience. The biggest nuclear weapon ever detonated had an energy of 40 megatons of TNT, or a cube the size of the Empire State Building. Our sample has the equivalent of 4,000 megatons. This is 4 billion tons of TNT, or a cube 1.3 kilometers high. To give you a sense of scale, this is the cube inside Manhattan. Once the sphere arrives on Earth, this super dense matter expands instantly and creates an explosion with the force of, well, the Sun. If we get the sample in Paris in the morning, the citizens of London would see what looks like a second sunrise, but one that gets brighter and brighter and hotter until London burns to ashes. In a radius of about 300 kilometers around the blast, everything would be burnt. The shock wave would travel around the Earth multiple times. Most buildings in Central Europe would be flattened, eardrums would rupture, and windows break across the continent. The explosion would be apocalyptic, possibly human civilization ending. If humans did survive, we could count on the dust blown into the atmosphere to create a small ice age. So, if there is one tiny bright side, it would be that the explosion might be an effective way to control human-caused climate change for a few decades. While this is definitely a good thing, all in all, we conclude that we should not try to bring the Sun to Earth. From hostile deserts to lonely islands and the highest mountains, wherever there is space to expand into, humans do so. So it's hardly surprising that we're already making preparations to set foot on Mars and to create the first permanent colony outside of Earth, maybe even terraform another planet and turn it into a second blue home. But wait, before we can get to the nice future stuff, we first have to complete the second phase of colonization, creating a semi-permanent outpost to prepare the ground for a larger human presence. But doing so will be gruesome. Even for an expansionist species like us, Mars is extreme. At first glance, Mars seems familiar. Polar ice caps, large valleys, liquid water under its surface, and a day barely longer than Earth's. The ideal place for us to go. Unfortunately, Mars is actually a cold, radioactive desert where the ground is poisonous and breathing is impossible. Mars is awful. You almost certainly don't want to go there. The pioneers doing the hard work on Mars will have an intensely stressful life filled with incredibly challenging problems never encountered before. But there are plenty of people willing to do that work, and we have the technology to enable them to do it. For this video, we will assume there have been prior missions to Mars to scout out a good place for an outpost, store resources and equipment, and that there's already a moon base that serves as a hub for Mars missions. The first major challenge for our outpost is the fact that Mars is very energy poor. Because of its distance from the Sun, solar power is only 40% as effective as on Earth. But even this weakened sunlight is often obscured for days by enormous dust storms. Solar power alone will probably not be enough. Alternatives such as wind power and geothermal energy are also unfeasible, as there's hardly any atmosphere and Mars's interior is much too cold. Initially, nuclear technology might be the only option. Since Mars doesn't have easily accessible radioactive elements, the nuclear fuel needs to come from Earth along with the reactor. If we do set it up, it could power our small outpost for the first few years. Unfortunately, all that energy won't be very useful if we can't breathe. Mars's atmosphere is only 1% as dense as Earth's and mostly made up of CO2. So our habitats need to be pressurized and filled with an artificial atmosphere made of nitrogen and oxygen, which comes with more problems. Corners and flat walls are weak points, so the habitats will have rounded and smooth shapes to handle the stress of great pressure differences between the interior and exterior. The airlocks need to be very airtight and work perfectly every time. Without an extensive magnetosphere or a dense atmosphere, half of all radiation coming from space reaches the ground. A person on the surface would be subjected to 50 times the radiation that they would be on Earth. 3 years on the surface of Mars exceeds the radiation dose limits imposed on NASA astronauts for their entire career. This increases cancer risks significantly. To prevent that, we could shield our habitats with a thick layer of frozen CO2 that can be harvested directly from the atmosphere. Covering the dry ice with a meter of dirt would further increase the level of protection. Sadly, this means almost no windows. From the inside, most living spaces will be windowless tunnels. From the outside, they'll look like burial mounds. All of this would still not hold back all the radiation, but reduce it just enough to be survivable for long periods of time. It won't, however, protect anyone who ventures outside. So remote-controlled robots will be used for routine work on the surface while our crew stays inside. Staying inside is a good idea for another reason: Mars dust. It's much finer than dust on Earth, so it could find its way into the gears or electronics of our machines. Because it's also very dry, it's electrostatically charged, sticking to everything, like spacesuits. It would be impossible to avoid carrying lots of Mars dust into our habitat and into the lungs of our crew. To make this even worse, Mars's soil is filled with very toxic perchlorate salts. Constant exposure could be deadly. This problem can still be overcome though. Spacesuits, for example, could be made in a way that they never truly enter the base but stay attached to the outside of the habitats. Okay, great. Now we've safely isolated humans in terms of energy and air and protected them from cancer, we just need to feed them. Water is easy to come by if a settlement is positioned near the Martian poles with their thick layers of ice. Growing food is a different kind of challenge though. Mars's soils are alkaline and lack the vital nitrogen compounds that plants need to grow. Before we can grow anything, we will have to decontaminate the soil, which is difficult and expensive. Then the soil can be fertilized using recycled biological waste. All of this will take a lot of time and is very energy intensive. So we might use aquaponics to raise fish and plants together, making the astronauts' diets more varied and tasty at the same time. This will be an important psychological boost for our overworked crew. All of these things don't solve one fundamental problem though. Mars has only 38% of Earth's surface gravity, which could cause muscle wasting, bone loss and cardiovascular problems. While this might be solved in the future by setting up rotating living spaces, for now our crew has to live with low gravity and exercise a lot to slow the degradation down. The crews will probably have to rotate every few years. After being stuck indoors in tight spaces without windows, with the same people, performing the same routines day in, day out, with little contact from the outside world and a lot to worry about. Like Antarctic scientists or submarine staff, they will undergo intense psychological screening to make sure they're mentally resilient enough to handle this lifestyle for several years. Establishing the first real infrastructure on Mars will be extremely taxing work that only a group of very determined and competent people can do. Luckily, we have enough of these on Earth. And there you have it, a small Mars base that will survive for at least a few decades. as long as it's getting a constant supply of resources, parts, nuclear fuel and crews from Earth. Unfortunately, Mars and Earth are separated by millions of kilometers and orbital periods that leave only a narrow travel window every 2 years. If there's an emergency in the colony, Earth wouldn't be able to help until the next travel window opens. Helpers may arrive on a planet filled with corpses. Settling Mars will be the toughest challenge we have ever faced. It will be gruesome work to establish the infrastructure we need. But we're stubborn and we like extreme challenges. If we push through Phase 2 of colonization, anything is possible. Cities illuminating the dark Martian night, a hub for travel between the planets, industries setting foot in orbit, terraforming, a true multi-planetary future. Going to Mars is hard, but worth it. And if we're lucky, we might be around long enough to see it happening and cheer on the people who take on these challenges for the benefit of us all. By the end of the 21st century, humanity is becoming desperate. Decades of heat waves and droughts have led to unusually poor harvests, while the warming oceans yield fewer fish each year. In the tropical zones, millions suffer from famines, and resource wars have made millions more flee to the north. As things quickly get worse, in an act of desperation, the world's governments decide to enact an emergency plan. It's far from certain that a grim scenario like this will play out, but the failure of world leaders to effectively address climate change makes it far from impossible. So, in the near future, it might become necessary to try something radical to slow down rapid climate change. Geoengineering. Interventions so massive in scale that they might undo centuries of human behavior, or make everything much worse. What is geoengineering? Is it really an option? And what if it goes wrong? Geoengineering methods vary from fantastic ones like constructing giant light sails in space to seeding clouds with salt, or wilder ones like fertilizing the oceans with iron to speed up the growth of trillions of algae cells. In this video, we'll focus on an intervention we could see during our lifetimes: stratospheric aerosol injection. A clunky term that means spraying stuff very high up in the atmosphere to keep the sun away. Keeping the sun away. CO2 doesn't heat up the planet on its own. Almost all of the energy on Earth comes from the sun in the form of electromagnetic radiation. About 71% of this energy is absorbed by the Earth's surface and atmosphere. This absorbed energy is emitted again as infrared radiation, and CO2 is able to trap this infrared radiation and keep it in the atmosphere for a while. You can compare this effect with snuggling under a blanket in the morning. Even in a really cold room, your body emits infrared radiation, and the air between your body and the blanket traps it and creates a warm and comfy feeling. So one way to cool down the planet would be to prevent energy from getting trapped under our planet blanket, which is already happening naturally. About 29% of the solar radiation hitting Earth is reflected back to space by bright surfaces like ice, deserts, snow, or clouds. More reflection, less energy, less warming. We can look at nature for inspiration. Specifically, the 1991 Mount Pinatubo eruption, the second largest volcanic eruption of the 20th century. Aside from massive devastation and almost 900 dead, scientists noted its strong impact on the global climate. The explosion ejected millions of tons of particles and gas as high as the stratosphere, which hung around there for a while. The stuff that's interesting for geoengineering is sulfur dioxide, a nasty-smelling and invisible gas. High in the atmosphere, it produced a haze of sulfuric acid droplets that mixed with water and created giant veils. These veils reduced the sunlight reaching Earth's surface by roughly 1%. Global average temperatures dropped by 0.5 degrees Celsius. It took 3 years until this cooling effect had stopped. Humans could imitate this process by injecting sulfur particles directly into the stratosphere. According to some scientists, this might be surprisingly easy to do, and we don't even need a lot of new technology for it. According to one study, it also might be pretty cheap compared with the costs of rapid climate change. A small fleet of specialized aircraft could ascend once a year and distribute aerosols along the equator from where they would be spread around the world. Projections assumed that injecting between 5 and 8 megatons of material per year would reflect enough sunlight to slow down or even stop global warming, giving us precious time to transition away from fossil fuels. Unfortunately, there might be a few unhappy side effects. There are a number of potential issues with aerosol injections. Rainfall patterns could change, which could negatively affect agriculture and cause famine. Billions of people could be affected in the worst case. Also, after the 1991 Mount Pinatubo eruption, the acid water veils not only cooled down the surface, they also heated up the stratosphere. As it turns out, acid is bad for the ozone layer, and the ozone hole over Antarctica was the largest it has ever been. Injecting sulfur particles over decades could have a similar effect. Scientists have already suggested using a combination of different minerals that might have much less harmful effects on the ozone layer, but more research and experiments need to be done to make sure this could work. But even if we don't damage the ozone layer, there are other risks. Politicians and industry might use the cooling effect as an excuse to delay the switch to a carbon-neutral economy. Even if geoengineering slows down global warming, humanity is still adding extra CO2 to the atmosphere. More CO2 in the air means that the oceans absorb more CO2, which makes them more acidic. This is already beginning to be deadly to huge ecosystems like coral reefs, and the longer this continues, the more severe the effects will be. But it gets worse. Once we start pumping particles into the atmosphere on a massive scale, we might be forced to do so for a long time, or we could risk a termination shock. What that means is that if humanity continues to enrich the atmosphere with CO2, but at the same time prevents the planet from heating up by blocking solar radiation, we're sitting on a time bomb. Once we stop geoengineering, the natural cycle will take over again and Earth would heat up. But after a few decades of keeping the planet artificially cold while still releasing massive amounts of CO2, it would heat up much quicker. An increase in temperature that would take 50 years today could happen in just 10 years. Such a temperature shock in such a short time would disrupt every major system on Earth so much that it would be impossible to adapt in time. The worst-case scenario could be dramatic famines and the rapid destruction of ecosystems. Humanity might survive, but the survivors would inhabit an unfamiliar and hostile world. The best-case scenario is that once the world has finally fully understood the existential danger of rapid climate change, geoengineering can buy us a crucial decade or two. Time to transition our economies and maybe even pull CO2 out of the atmosphere, maybe with technologies that we'll discuss in a future video. Conclusion. Geoengineering is a scary concept. It's not a solution to climate change, and it might even be a welcome excuse for the fossil fuel industry to delay the end of the fossil fuel age. Over the last few decades, geoengineering has been so controversial that it's stopped many scientists from doing the experiments necessary to understand it better. But blankly opposing geoengineering is short-sighted. The sad truth is, we are already running a geoengineering experiment. We're testing how fast the world changes if we add about 40 billion tons of CO2 each year. This experiment is about to get really exciting. Hopefully, we'll never have to use geoengineering. But if we need to in the future, we better have done the science. We better be prepared. Or a panicking humanity might accidentally press the self-destruct button. Planet Earth is the home of every life form known to us in the universe. Its age is about a third of the age of the universe, and, admit it, it is a thing of beauty. A slightly squashed sphere with a heavy metal core and a lighter surface crust wrapped in a thin sliver of sweet air to breathe, with vast oceans, fertile plains, magnificent mountains, freshwater rivers, streams, lakes and aquifers, orbiting a star which warms us and gives us energy. But how did our home come into existence, and what's it made of? $4.6 billion years ago, Earth was created from the remnants of dead stars that collected in a giant dirty gas cloud. The gas cloud became denser in its center and formed an accretion disk. Small particles started clumping together and building larger and larger objects until they formed the objects we call planets today. This process took 10 to 20 million years and is still not very well understood. At about this time, when the solar system was young and chaotic, a giant object about as big as Mars collided with our home. The impact was violent, and if the object had been more massive, it might have destroyed Earth. Material from Earth was smashed out into orbit and formed the Moon, which is the biggest satellite in relation to its planet in the solar system. At this time, Earth was a hot hell, constantly being hit by asteroids, with seas of lava and a toxic atmosphere. But something was about to change drastically. Earth cooled down. Water from the inside of the Earth wandered to the surface and rained down on Earth, only to vaporize again and become clouds. Millions of asteroids brought more and more water to our planet. All the water on Earth has about this volume compared to Earth. Today, the surface of Earth is 71% water and 29% land. 97.5% is saline water, while only 2.5% is freshwater. The freshwater is 69% ice and snow, 30% are groundwaters, and only about 1% make up the remaining groundwaters. But even this small part is mostly frozen. Only a tiny part of our water is actually lakes and rivers, and an even tinier part is bound in living things. So, gradually the Earth cooled down and the surface formed a thin crust. But inside the Earth, hot rock continued to swirl about, moving the crust from below and breaking it apart. This process is called plate tectonics and is happening right now. We'll make a whole video about it in the future. For now, let's just say that the crust of Earth consists of separate giant plates that move around. As they meet, they crumble and create mighty mountains, or violently plunge back down deeper into Earth, creating deep trenches. That's the way the highest place on Earth was formed, Mount Everest, and the deepest, the Mariana Trench. From our perspective, Earth's mountains and trenches are mighty indeed, but when you look at the Earth in cross-section, you can see how tiny they actually are. The part we stand on is the crust, which is about 50 kilometers thick, though it can vary between 5 and 70 kilometers. By the way, the deepest hole ever drilled by man is 12.262 kilometers deep. After the crust comes the mantle. It's a silicate rocky shell and about 2,900 kilometers thick. The mantle consists of the upper mantle and the lower mantle. The upper mantle has different regions too. Its upper part, which is viscous and carries the crust, is called the lithosphere. After that, there comes the asthenosphere, which consists of less mobile, mostly solid material. The lower mantle reaches deep down to the outer core of Earth. Earth's outer core is a liquid layer of iron and nickel, about 2,266 kilometers thick. Temperatures vary from 4,000 degrees Celsius to 5,700 degrees Celsius. And in the center is the inner core. It's mostly solid, a ball made of an iron-nickel alloy, with a radius of about 1,200 kilometers, 70% the size of the Moon, and about the temperature of the surface of the Sun. It is slowly growing at an estimated rate of about 1 millimeter per year. Now for some perspective. This small layer of crystallized milk products of former molten mantle is where we live. Then there's Earth's magnetic field. It's an invisible phenomenon that diverts high-energy particles coming from the Sun and other sources, allowing for a stable environment with comparatively little radiation impact on Earth. But why is it there? Actually, we don't really know a terrible lot about that. We know it has something to do with the core of the Earth. Inside this metal sphere, large electrical currents flow in complicated patterns. They cause a magnetic field that sort of stabilizes itself according to the laws of electrodynamics. This entire system is called the dynamo. But don't let us fool you into thinking we have it all figured out. Speaking of breathtaking information, what about the airy stuff that surrounds us? By volume, dry air consists mostly of nitrogen, oxygen, argon, carbon, a variable amount of water vapor, and small amounts of other gases. Humans are very dependent on the lowest layer of the atmosphere, the troposphere, where the weather is. It's 12 kilometers thick on average. Above that is the stratosphere, which is where the ozone layer protects us from the sun's most aggressive type of light. Above that is the mesosphere, the coldest place on Earth, with an average temperature around minus 85 degrees Celsius. At about 80 kilometers up, the thermosphere starts. The transition to space is a fluent one without clear borders, but humans decided that space starts here. At about 100 kilometers, Earth stops and space begins, though the atmosphere extends a bit further. In this region we find the ionosphere, the aurora borealis, and the ISS. And the outermost layer is the exosphere, stretching up to 10,000 kilometers. It merges fluently with outer space where there's no atmosphere at all. The atoms and molecules in this area are so far apart that they can travel hundreds of kilometers without colliding with each other. Okay, humans in their present form have only been around for 200,000 years. That's 0.004% of Earth's history. Not long really. And here we are now, living in a thin moist layer on a small wet rock. We call this rock Earth. It is the product of the universe's deepest workings, the result of a constant process of creation and destruction, happening all over the universe all the time, helped by chance, the laws of the universe, and random events. We are really lucky. 3 reasons why we should stop using nuclear energy. 1. Nuclear weapons proliferation. Nuclear technology made a violent entrance onto the world stage. Just 1 year after the world's first ever nuclear test explosion in 1944, 2 large cities were destroyed by just 2 single bombs. After that, reactor technology slowly evolved as a means of generating electricity, but it's always been intimately connected with nuclear weapons technology. It's nearly impossible to develop nuclear weapons without access to reactor technology. In fact, the Nuclear Non-Proliferation Treaty serves the purpose of spreading nuclear reactor technology without spreading nuclear weapons with limited success. In 40 years, 5 countries have developed their own weapons with the help of reactor technology. The fact of the matter is that it can be very hard to distinguish a covert nuclear weapons program from the peaceful use of nuclear energy. In the 1970s, the big nuclear powers were happily selling peaceful technology to smaller countries, which then developed weapons of their own. The road to deadly nuclear weapons is always paved with peaceful reactors. 2. Nuclear waste and pollution. Spent nuclear fuel is not only radioactive, but also contains extremely poisonous chemical elements like plutonium. It loses its harmfulness only slowly over several tens of thousands of years. And there is also a process called reprocessing, which means the extraction of plutonium from spent nuclear fuel. It can be used for 2 purposes, to build nuclear weapons or to use it as new fuel. But hardly any of it is used as fuel because we don't have the right kind of reactors for that. A milligram will kill you, a few kilograms make an atomic bomb, and even an inconspicuous country like Germany literally has tons of the stuff just lying around because reprocessing sounded like a good idea decades ago. And where will all the waste go? After dumping it into the ocean was forbidden, we've tried to bury it, but we can't find a place where it will definitely stay secure for tens of thousands of years. Over 30 countries operate nearly 400 reactors, managing several hundred thousands of tons of nuclear waste, and only 1 is currently serious about opening a permanent civilian waste storage: tiny Finland. 3. Accidents and disasters. Over 60 years of nuclear power usage, there have been 7 major accidents in reactors or facilities dealing with nuclear waste. 3 of those were mostly contained, but 4 of them released significant amounts of radioactivity into the environment. In 1957, 1987 and 2011, large areas of land in Russia, Ukraine and Japan were rendered unfit for human habitation for decades to come. The number of deaths is highly disputed, but probably lies in the thousands. These disasters happened with nuclear reactors of very different types in very different countries and several decades apart. Looking at the numbers, we may as well ask ourselves, are 10% of the world's energy supply worth a devastating disaster every 30 years? Would 30% be worth another Fukushima or Chernobyl somewhere on Earth every 10 years? What area would have to be contaminated so we say no more? Where is the line? So, should we use nuclear energy? The risks may outweigh the benefits, and maybe we should stop looking into this direction and drop this technology for good. If you want to hear the other side of the argument, or a short introduction to nuclear energy, click here. The Sun. Smooth and round and peaceful. Except when it suddenly vomits radiation and plasma in random directions. These solar flares and coronal mass ejections, or CMEs, can hit Earth and have serious consequences for humanity. How exactly do they work? How bad could they be? And can we prepare for them? While the Sun seems pretty solid, it's actually like a very hot ocean. So hot that it rips atoms into electrons and nuclei, all flowing around each other in a plasma. This plasma is pushed around and shaped by the Sun's magnetic field, similar to how the Sun's gravitational field reaches out to the planets and shapes their orbits. But magnetism is very different from gravity. Magnetism is one part of a dual force, electromagnetism. Electricity creates magnetic fields, and magnetic fields create electricity. On the Sun, the plasma made of electrically charged protons and electrons creates a magnetic field as they move, and this magnetic field then shapes the flow of particles. They're stuck in a dynamic feedback loop called a dynamo, which keeps the Sun's magnetic field alive. This magnetic field stores enormous amounts of energy and leaks out over the solar system. It carries with it a constant trickle of solar plasma like a light rain known as the solar wind, creating a sort of space weather. But it isn't always calm and smooth. As the Sun's plasma churns and flows around itself, its magnetic field gets all kinked and twisted. This creates magnetic knots that build up enormous amounts of energy. When the magnetic knots break, like a tangle of springs exploding outwards, the Sun can vomit plasma and other awful things into the solar system. These solar storms come in many types, like solar flares, a tidal wave of high-energy radiation. They race through the solar system at the speed of light, sweeping up protons in the solar wind, accelerating them into a high-speed solar proton storm. Then there are coronal mass ejections, which rip millions or billions of tons of plasma from the Sun's atmosphere, catapulting it through the solar system at speeds of up to 9 million kilometers per hour. When these monsters hit us, nothing happens on Earth. While even smaller storms can damage satellites, affect radio communication, or be dangerous to astronauts, for people on the surface, space weather is harmless. Earth's atmosphere protects us from the worst effects of a solar flare by absorbing the blast of X-rays high up in the atmosphere, well before it reaches the surface. The electrified plasma from a CME is deflected by the Earth's magnetic field, diverting the energy storm to the north and south poles, where energetic particles fall into the atmosphere, causing the atmosphere to glow and creating beautiful auroras. As with any sort of weather, most of the time things are fine. Sometimes there are hurricanes though, or in the case of the Sun, solar superstorms. And we know that they happen once or twice every century. If one were to happen today, we would first detect strong solar flares, a sort of flash before the much more dangerous thunder. The thunder is a CME, consisting of billions of tons of hot magnetic plasma that crosses the 150 million kilometers between the Sun and Earth in less than a day. When it arrives, it causes a shock wave that violently compresses the Earth's magnetic field and transfers energy into the magnetosphere. But it can get worse. If the magnetic field of the CME is aligned to Earth's in just the right way, the two magnetic fields merge. As the magnetic cloud passes over Earth, it stretches the Earth's field into a long tail. Eventually, the energy stored in the tail becomes too much to contain. It snaps and explosively releases its energy towards Earth. A geomagnetic storm has begun. A few hundred years ago, nobody would have cared. This storm gushing over the Earth is not relevant for machines made out of meat and bones. But it's very relevant for machines made out of metal and wire. Remember the dynamo? Magnetism creates electric currents. Earth in the 21st century is covered in millions of kilometers of wires transporting electricity and a complex grid of machines like transformers that make this transfer possible. A CME's energy can induce currents in our power grid that can either completely shut it down or, worse, destroy the transformer stations that keep our grid running. This has happened already, like when the Quebec power grid failed after a strong solar storm in 1989. But in general, our engineers know how to deal with these storms, and so we usually don't even notice. The last time a solar hurricane washed over Earth was in 1859, the Carrington event, the largest geomagnetic storms ever observed on Earth. massive auroras occurred as far south as the Caribbean. In some places, they were so bright that people got up thinking the sun was rising. Luckily, we only had one sort of modern technology: telegraph systems. They failed all over the world, shocking their operators and chucking out sparks. Today, we have a tad more technology, and our luck may run out soon. Another bad solar storm is bound to happen eventually. A storm as strong as the Carrington event missed Earth only by a small margin in 2012. Studies projected that it would have inflicted serious damage to electronic systems globally, costing up to $2.6 trillion to the US alone. The time to replace all the damaged systems was estimated at between 4 and 10 years. It's hard to say how bad it could have been. Experts disagreed. Some assumed there would just be temporary blackouts, but others worried it could be much worse. We won't know for sure until a big solar hurricane hits us. The probability of such an event is estimated to be 12% per decade. That's about a 50-50 chance of at least one in the next 50 years. And there is more unsettling news. A 2019 paper found that even calm stars like our Sun can create superflares every few thousand years. Eruptions orders of magnitude stronger than the strongest storms we have observed in the solar system. If such a storm hits us unprepared, the consequences could be catastrophic. It's hard to overstate how much we depend on electricity. It's not just the lights at home, it means no computers, no communication, no navigation. A sustained power outage might lead to a breakdown of the supply chain, water supply systems failing, and hospital generators running dry. Supermarkets not being refilled while food rots in the fields. The lack of power might make it extremely hard to reboot our broken power grid, taking years or decades to restart our starving civilization. Okay, time to panic. As much as daily newspapers might like for solar storms to send us back to the Stone Age, they probably won't. Fortunately, even though solar storms aren't preventable, virtually all of their nasty side effects are. Scientists observing the sun have a few hours up to a few days to see a CME coming. And the engineers working the systems that keep the world running are well aware of the risks posed by solar storms. Transformers and substations can be taken offline. Short preventative blackouts, or in other words, by unplugging stuff. Engineers can open up extra lines to dissipate the extra power. And with investment and upgrades cheap compared to those other natural disasters require, we could protect the world's electric grid against even the nastiest of storms. But we do need to prepare. While the risk is manageable, it is real. For while our sun bathes us in warm and pleasant light, one day it might send a monster our way that we better be ready for. We are prisoners on Earth. The universe taunts us by showing us all the places we can't ever visit. However, if our species wants to have a long-term future, we have to escape our prison. But what's keeping us here in the first place? Turns out we owe the universe a debt that is 4.5 billion years old. Everything with mass in the universe attracts every other thing with mass. We call this phenomenon gravity. The closer you are to a big chunk of mass, the stronger the attraction, or the more you're pulled in. This effect traps us on Earth. We can imagine this as being prisoners in a gravity prison or a gravity well. It's not a literal well, but a handy concept to understand how this works. Being in a gravity prison means that you owe gravity energy. But how can you owe energy? Because in our universe, things don't want to change their speed or direction. To convince them to move, you have to expend energy. Billions of years ago, the gravitational attraction of trillions of dust particles orbiting our sun pulled them together until they formed a planet. This process used energy and created the gravity well we're now a part of. The deeper you are inside a gravity well, the more energy you owe gravity. If you don't find a way to get enough energy, you're not able to leave, no matter what you do. Because your atoms were once part of the dust that the universe expended energy on to get to this place. Okay, let's summarize all of that again. Objects in the universe don't like to move. You have to convince them to do so with energy. Gravity used energy to convince the parts that make up our planet to move together. This created a gravity prison in the process, trapping us. To escape it, we need to repay it with energy. Okay, how do we do that? To get into space, we need to go through a complicated process of exchanging energy. For this purpose, we build negative potential energy repaying machines, known by their more boring name, rockets. Rockets work by using some of the most energetic chemical reactions humans know about to basically explode fuel in a controlled way. This converts chemical energy into kinetic energy. The exhaust of the reaction is directed outwards and pushes the rocket away from Earth. By expending a lot of energy, we are increasing our gravitational potential energy, which is a complicated way to say that we're paying back our energy debt to gravity. But it's actually a lot trickier than that. When you burn fuel to get into orbit, you lose lots of energy to heat, the exhaust and atmospheric drag, so you actually need much more. And you can't just pile a huge amount of really explosive, dangerous fuel close to your payload and detonate it. You need a controlled burn, which is complicated and makes your rocket very heavy, which means it has more mass. The more mass something has, the more energy you need to convince it to move. So you need more fuel to lift up your rocket. But if you need more fuel, that means you need more rocket to carry that fuel. But this makes your rocket heavier, thus requiring more fuel, which requires more rocket to carry that new fuel, and so on. At the end of this madness, you need closer to 100 times the weight of your payload to launch. Ariane 6, for example, the European rocket, will weigh 800 tons and should be able to transport 10 tons into geostationary transfer orbit or 20 tons into medium Earth orbit. But a rocket can only produce so much thrust, so there's a maximum weight after which it just won't take off. If you add too much weight, it won't lift off, so you can't just build bigger and bigger fuel tanks. This is the tyranny of the rocket equation, and it means spaceflight will never become easy. But wait, it gets worse. Getting to space is still not good enough. You're still inside the gravity prison at the edge of space and will crash back to Earth. Staying in space is much harder than getting there. To get to a stable position where it can stay for a while, a rocket has to reach low Earth orbit. To do this, you need a lot of kinetic energy, which means going extremely fast. At an altitude of about 100 kilometers, this is 8 kilometers per second, 28,000 kilometers per hour. Fast enough to travel around Earth in 90 minutes. Here, we can use a trick. Instead of flying straight up, we can go sideways. Earth is a sphere, so if you're going sideways fast enough, even though you're falling towards Earth, the ground will curve away beneath you. So as long as you're above the atmosphere, about 100 kilometers up, you'll be able to stay up there in orbit. This is what the ISS does, falling around Earth, expending energy from time to time to stay fast enough. If we look at orbits in scale, we see that near-Earth orbit is laughably close to Earth. To deploy, for example, satellites or leave for other planets requires another round of energy debt repayment. Getting to orbit is the most difficult part of spaceflight for us right now. For example, if we want to send a rocket to Mars, half the energy is necessary just to get into orbit, and the other half for the 55 million kilometers to Mars. Therefore, to be as effective as possible, rockets aren't built in one giant piece. Instead, we use multi-stage rockets. You don't need to carry an empty fuel tank, so rockets drop it. Rockets today shed their boosters and main stage as they ascend, with each successive stage being its own fully contained rocket, complete with its own engine and fuel. Okay, so this is why getting to space is hard. If you feel all of this seems really complicated, don't worry. It's literally rocket science. This video was made possible in part by a sponsorship by Airbus Safran Launchers and Arianespace, who are getting their new Ariane 6 rocket ready to launch into space in 2020. You can learn more about the rocket here. Have you ever been in an argument about nuclear power? We have, and we found it frustrating and confusing, so let's try and get to grips with this topic. It all started in the 1940s. After the shock and horror of the war and the use of the atomic bomb, nuclear energy promised to be a peaceful spin-off of the new technology, helping the world get back on its feet. Everyone's imagination was running wild. Would electricity become free? Could nuclear power help settle the Antarctic? Would there be nuclear-powered cars, planes, or houses? It seemed that this was just a few years of hard work away. One thing was certain: the future was atomic. Just a few years later, there was a sort of atomic age hangover. As it turned out, nuclear power was very complicated and very expensive. Turning physics into engineering was easy on paper, but hard in real life. Also, private companies thought that nuclear power was much too risky as an investment. Most of them would much rather stick with gas, coal and oil. But there were many people who didn't just want to abandon the promise of the atomic age, an exciting new technology, the prospect of enormously cheap electricity, the prospect of being independent of oil and gas imports, and in some cases, a secret desire to possess atomic weapons provided a strong motivation to keep going. Nuclear power's finest hour finally came in the early 1970s, when war in the Middle East caused oil prices to skyrocket worldwide. Now, commercial interest and investment picked up at a dazzling pace. More than half of all the nuclear reactors in the world were built between 1970 and 1985. But which type of reactor to build, given how many different types there were to choose from? A surprising underdog candidate won the day: the light water reactor. It wasn't very innovative, and it wasn't too popular with scientists, but it had some decisive advantages. It was there, it worked, and it wasn't terribly expensive. So, what does a light water reactor do? Well, the basic principle is shockingly simple. It heats up water using an artificial chain reaction. Nuclear fission releases several million times more energy than any chemical reaction could. Really heavy elements on the brink of stability, like uranium-235, get bombarded with neutrons. The neutron is absorbed, but the result is unstable. Most of the time, it immediately splits into fast-moving lighter elements, some additional free neutrons, and energy in the form of radiation. The radiation heats the surrounding water, while the neutrons repeat the process with other atoms, releasing more neutrons and radiation in a closely controlled chain reaction. Very different from the fast, destructive runaway reaction in an atomic bomb. In our light water reactor, a moderator is needed to control the neutron's energy. Simple, ordinary water does the job, which is very practical since water's used to drive the turbines anyway. The light water reactor became prevalent because it's simple and cheap. However, it's neither the safest, most efficient, nor technically elegant nuclear reactor. The renewed nuclear hype lasted barely a decade though. In 1979, the 3 Mile Island nuclear plant in Pennsylvania barely escaped a catastrophe when its core melted. In 1986, the Chernobyl catastrophe directly threatened Central Europe with a radioactive cloud, and in 2011, the drawn-out Fukushima disaster sparked new discussions and concerns. While in the 1980s, 218 new nuclear power reactors went live, their number and nuclear's global share of electricity production has stagnated since the end of the 80s. So what's the situation today? Today, nuclear energy meets around 10% of the world's energy demand. There are about 439 nuclear reactors in 31 countries. About 70 new reactors are under construction in 2015, most of them in countries which are growing quickly. All in all, 160 new reactors are planned worldwide. Most nuclear reactors were built more than 25 years ago with pretty old technology. More than 80% are various types of light water reactor. Today, many countries are faced with a choice: the expensive replacement of the aging reactors, possibly with more efficient but less tested models, or a move away from nuclear power towards newer or older technology with different cost and environmental impacts. So, should we use nuclear energy? The pro and contra arguments will be presented here next week. Subscribe, and then you won't miss it. In the 1970s, thousands of chicken heads rained from the sky in Europe, making foxes and other wildlife confused and very happy. Why? They were filled with a vaccine to fight the deadliest virus known to humanity. Since the 1930s, a rabies epidemic had been sweeping across wildlife populations in Europe, and humans wanted to finally get rid of the virus once and for all. Rabies is named after Lyssa, the ancient Greek spirit of mad rage, and has been haunting us for at least 4,000 years. It can turn animals into angry beasts and humans into zombies that fear water. But what makes Lissa fascinating is not just how bizarre and deadly its infection is, but also how incredibly good it is at avoiding our defenses. Viruses exist on the edge between life and death, hardly more than a few genetic instructions that need living cells to multiply. The Lissa virus is simple even for a virus. It has only 5 genes, that is, the instructions for 5 proteins that let it solve complex problems: infect a mammal, avoid its immune system, travel to its brain, make more of itself, and infect new hosts. Let's see what happens if you get infected. It all starts with a bite, most likely by a dog carrying millions of viruses in its saliva, pushing them deep into the tissue. The goal is your nerve cells, your neurons. They are living electrochemical wires transferring signals throughout your body and can stretch for up to 1.5 meters with their cellular machinery on one end and a terminal on the other. The terminal is where cells talk to each other by passing chemicals that convey information. Lissa probably binds to the receptors that are crucial for this process and slips inside the unsuspecting nerve cells. Inside, the virus has to solve a big problem. It needs to get to the cellular machinery to take over the cell and make more viruses, and because neurons are pretty long, this can be far away. There is a solution at hand though. Cells have microtubules spanning their insides that give them structural integrity, but they also provide a track system for a specialized delivery system. Dynein motors are actual motors that use energy and deliver packages. They're made from 50 different proteins, 10 times more than the virus, and look like a little pair of shoes. Lissa uses one of its 5 proteins to hijack this amazing system and order it to head for the nucleus. What's the immune system doing to prevent all of that? Well, unfortunately, not much. Usually when a virus attacks, your civilian cells are crucial in activating your immune response. They notice that they've been infected and release hundreds of thousands of a special family of proteins, the interferons that, well, interfere with viruses. We'll have to simplify a lot, but in a nutshell, interferons alert your immune system to make antivirus weapons. But they do much more. They tell civilian cells to turn down their protein factories for a while, which means that viruses can't replicate efficiently anymore. And interferons tell your cells to become super transparent, which is important because how can your immune cells notice that your civilian cells are infected when viruses hide inside them? Your body solves this by creating display windows into their insides called MHC class I molecules. Cells constantly produce stuff to stay alive, and to showcase to your immune cells what's going on inside them, they take random samples of their products and put them into these tiny display windows to give a peek inside. Interferons tell your cells to make way more display windows and become super transparent. If a cell is infected and forced to make virus parts, your immune cells will see these parts in a window and order the infected cell to kill itself and all the viruses trapped within. This is one of the most powerful methods of wiping out a viral infection. Unfortunately, Lissa blocks your neurons from making interferons and stays basically invisible to your immune system. In contrast to many other viruses, when it replicates, it doesn't kill its host, which would also trigger alarm systems. Instead, it stealthily jumps from neuron to neuron, very slowly making its way to your brain. This phase can take weeks to months and very rarely even years, and depends on a bunch of things, like if the bite was in your face or foot, or how many viruses got into your muscles. Lissa is a patient monster, until it reaches its goal, your brainstem. Finally, the immune system catches on that something isn't right and reacts. It dispatches some of your most powerful antivirus cells, killer T cells, to seek and kill infected cells and wipe out the enemy. In other viral infections, this would be a turning point, but in rabies, the T cells are rushing towards their doom. Simple Lissa, with its 5 proteins, plays a reverse card, using the immune system's ingenuity against itself. Your central nervous system is a very fragile part of your body, and so the immune system has to be very careful. A few haywire immune cells in your brain is a quick way to die. So they aren't free to enter your nervous system, they have to be invited in and can be kicked out. To protect themselves, your nerve cells can order T cells to self-destruct if they think they're overreacting. and Lissa figured out a way to make infected neurons express this order. So as your powerful defense cells arrive, they are ordered to commit suicide. Now the virus infiltrates the brainstem. Once this stage is reached, you are going to die. How Lissa kills. One of the most irritating things about the Lissa virus is that we still don't know exactly how and why an infected person dies. Our usual idea of viruses causing damage is by multiplying rapidly, killing their host cells once they've made enough copies, triggering a massive immune reaction that also does a lot of damage. But this doesn't seem to be what happens here. Brain tissue of rabies patients shows minimal, sometimes non-existent damage. Instead of murdering everything in sight, it's currently thought that Lissa wreaks havoc by messing up the neuron communication inside your brain, so much so that it can't function anymore. This leads to symptoms like confusion, aggression, and paralysis. Now the virus begins to leave. Still traveling through neurons, it migrates away from the brain and heads for the salivary glands. This is remarkable because after traveling in one direction, the virus reverses its course. After decades of study, we don't know how this works. Lissa ends up saturating your saliva, ready for the irate mammal to bite another and repeat the cycle. While this seems like the beginning of a zombie outbreak, luckily there are no known cases of a human biting another and spreading rabies this way. Now, the end is near. You are rapidly developing encephalitis, a swelling of the brain with many unpleasant neurological symptoms from lethargy to paralysis. Slowly at first, and then suddenly, organ after organ fails as you slip into a coma. There is no known effective therapy. Barely anyone has ever survived Lissa once symptoms begin to show. It is by far the deadliest virus we know. Except there is actually something that could save you: a vaccine. Rabies was one of the first diseases humans developed a vaccine for. As vaccines do, it prepares your immune system for a future attack so it has the right weapons ready in high numbers. The horrific tricks of simple Lissa don't work once you are vaccinated. And the vaccine is special for another reason. Because Lissa is so slow in the first few weeks, it can be given to you after you've been exposed. So you can still be vaccinated after you've been bitten by an animal. Which is super important if you've had contact with a sick wild animal, say a bat, because you often don't even notice a bite from tiny teeth. Rabies is a monster, one that has followed our species around for thousands of years, that our ancestors were terrified of, and rightly so. It still kills around 60,000 people each year, almost half of them children. We are far from eradicating this monster. It lurks in the shadows, in forests and animals of all kinds, ready to return in greater numbers if we ever forget how to keep it at bay or if we continue the trend of being suspicious of vaccines. Let's hope that one day humanity slays this monster, so it can become, like most monsters, part of our imagination. The Earth is a gigantic ball of semi-molten rock with a heart of iron as hot as the surface of the Sun. Titanic amounts of heat left over from its birth and the radioactive decay of trillions of tons of radioactive elements find no escape but up. Currents of rock spanning thousands of kilometers carry this energy to the surface. Earth's crust is the only thing in their way. It feels solid to us, but it's only a fragile barrier, an apple skin around a flaming behemoth. True apocalypses can break through and unleash eruptions tens of times more powerful than all of our nuclear weapons combined, subjecting the climate to centuries worth of change in a single year, while drowning continents in toxic ash and gases. Supervolcanoes. How big can they get? And will they put an end to humanity? Volcanoes. There are many types of volcanoes, from towering mountains to lava domes, but they have two main sources. The first is at the boundaries between tectonic plates, the pieces of the crust that cover the Earth like a giant jigsaw puzzle. There are 7 major tectonic plates and dozens of smaller ones, drifting against each other at up to 15 centimeters per year. This sounds slow, but on geological timescales, it is a titanic struggle over who gets to stay on the surface. The winning plate crumples into a new mountain range, while the loser is shoved underneath into an ocean of hot rock at 1,300 degrees Celsius, the asthenosphere. The temperature here is enough to melt rock into a liquid, but the insane pressures of all that mass keep it a superheated solid. Tectonic plates are usually in contact with water for thousands of years and absorb some of it. When they're submerged into the hot underworld, this water triggers chemical transformations that allow tiny portions to melt into magma. Liquid magma is less dense than solid rock, so it rises to the surface in furious bubbles that accumulate in sponge-like reservoirs right under the crust. If enough magma accumulates, it becomes powerful enough to pierce through the crust, which we experience as volcanoes. This happens under the winning plate, like a revenge attack by the loser before it's erased forever. The second main source of volcanoes are thought to be mantle plumes. These are columns of abnormally hot rock that rise all the way from the planet's core mantle boundary to the surface. Much less is known about them, but in a way, it's as if the Earth's mantle has weather patterns and mantle plumes are a little like hot air rising to form storm clouds. Storms hundreds of millions of years old, made of rock circulating at a rate of a few millimeters per month. They don't care about the motion of tectonic plates, so they can break the crust to create volcanoes in the middle of nowhere that stubbornly stay active as the crust shifts around them. The volcanic boom meter. Scientists love to put big booms on a scale and came up with a logarithmic scale that measures the volume ejected during an eruption. The Volcanic Explosivity Index, or VEI. Simply put, it starts really small and gets very big very quickly. A VEI2 eruption would fill 400 full Olympic swimming pools with lava. We have around 10 of these per year. At VEI3, we already see devastating effects, like the eruption of the Semeru volcano in 2021 that destroyed thousands of homes in Indonesia. At VEI5, we see catastrophic amounts of materials, cubic kilometers of debris, equivalent to an entire lake of molten rock blasted into the air. Like the 2022 Hunga Tonga Hunga Hapai eruption that sent a shockwave around the globe many times and created ocean-wide tsunamis. At a VEI of 6, an eruption can change the world. In 1883, the Indonesian island volcano Krakatoa erupted nearly continuously over the course of 5 months. One of those eruptions blew it apart, producing the loudest sound recorded in history, 10 trillion times louder than a rocket taking off, heard halfway around the world. 30-meter-high tsunamis swept away nearby populations, and so much gas and ash were released that global temperatures cooled by nearly 0.5 degrees Celsius. Red, dusty sunsets followed for many years. At VEI7, we get supercolossal eruptions, millennium-defining events that human civilization has only encountered a handful of times. Mount Tambora was a 4,300-meter-high mountain until it exploded in 1815 and released 400 times more energy than the Tsar Bomba. 140 billion tons of ash and dust were shot halfway to space before smothering the world's skies, turning them a sickly yellow. There was no summer the following year, crops died, and over 100,000 people perished. This is the dreadful potential of volcanic eruptions, with famines across the other side of the world and even centuries-long cold periods being attributed to them. Okay, but what's a supervolcano? The term supervolcano is a media invention and not a scientific term. The main issue with them is that not every eruption from a supervolcano is a super eruption. What makes supervolcanoes special is that they've been waiting to erupt for hundreds of thousands of years. Pressure builds up in colossal magma reservoirs several kilometers deep until it becomes strong enough to lift the rock above it by several meters. Rocks crack under the pressure until they finally give way and billions of tons of gas and ash blast out at supersonic speed. An insane explosion of at least 1,000 cubic kilometers that impacts every corner of the globe. And yet, that is only a small portion of the magma reservoir. Super eruptions are like a boiling pot of water popping its lid off and spilling a bit off the top. Afterwards, the ground collapses into the void left behind, forming a hole called a caldera. Under this caldera, pressure starts building again until the volcano gathers enough energy for another super eruption. But this could take hundreds of thousands of years. It's estimated that one of the few volcanoes capable of super eruptions on Earth could cause a catastrophic eruption every 17,000 years on average. That would make them far more frequent than comparable asteroid impacts. The most recent super eruption is the Oronui eruption 26,500 years ago in New Zealand. With the force of dozens of billions of tons of TNT, a Mount Everest-sized pile of explosives, a huge portion of the landscape was scooped out and thrown into the atmosphere. It left behind a caldera spanning 20 kilometers, and it caused the entire southern hemisphere to undergo a period of abrupt cooling. Though among super eruptions, it's a mere firework. The Lake Toba eruption of 74,000 years ago was a much more significant turning point in history. It released a gargantuan 5,300 cubic kilometers of material, enough to blanket parts of South Asia in 15 centimeters of ash and trigger a rapid 4 degrees Celsius drop in global temperatures. It's possible that the volcanic winter lasted 10 years, followed by worldwide droughts for centuries. Earth's climate might have not recovered for 1,000 years. The largest volcanic events we know of were not really huge explosions, but floods of millions of cubic kilometers of lava. The grand finale were the Siberian traps around 250 million years ago, a continuous release of lava for 2 million years. They raised the ocean temperatures to over 40 degrees Celsius, which caused the Permian-Triassic extinction, killing over 90% of all species. Earth's surface needed 9 million years to recover. These sorts of eruptions don't change the climate, they are the climate. But thankfully, we haven't seen anything even remotely close to that scale in many millions of years. So, should you be scared of supervolcanoes? Definitely not. They've been used to frighten many people and are overhyped as an unavoidable apocalypse. The most famous one, Yellowstone, will erupt again, but they will be relatively small eruptions. Natural disasters for sure, but not enough to devastate the US or come close to ending humanity. The chance of a VEI-8 eruption in the next few hundred years is less than 2%, and more importantly, it wouldn't come as a sudden surprise. However, less powerful but more frequent eruptions can also do serious damage to our civilizations and are in many ways a much greater concern. So we must watch for slow changes in magma reservoirs like ground swelling and temperature increases to get an early warning that can save the lives of people living the closest to a volcano. And there's time to develop solutions that can remove sulfur and ash from the stratosphere to eliminate the root cause of the climate disruption we've seen from previous eruptions. Who knows, maybe we'll even be able to turn this force of destruction into an agent for good by exploiting the geothermal energy held in their giant magma reservoirs. We've done this work for so many other disasters, and we are already doing things we could only have dreamed about decades ago, like sending a probe to perform our first asteroid redirection test. With determination, humanity really can solve anything. So while deep below us an angry hell is churning and waiting for its moment, you can sleep well tonight. Casually watching a video on YouTube on a computer more powerful than anything humanity could build a few decades ago. This progress and all the wonderful machines you take for granted are built on a few rare and precious materials with names like terbium, neodymium, or tantalum. Getting these rare materials from the ground into your devices is ugly. The mining industry is responsible for air and water pollution and the destruction of entire landscapes. Dangerous chemicals like cyanide, sulfuric acid, or chlorine are used to extract the resources, harming biodiversity, workers, and locals. And rare resources are also political tools when countries restrict access to them to get their way. But what if we could replace the mining industry on Earth with a clean process that can't harm anyone? Well, we can. All we need to do is look up. Asteroids are millions of trillions of tons of rocks, metals, and ice, leftovers from the cloud that became the planets 4.5 billion years ago. They can be as small as a meter or protoplanets the size of entire countries. Most of them are concentrated in the asteroid belt and the Kuiper belt, while hundreds of thousands more do their own thing between the planets. As space travel is becoming more feasible, scientists and economists have begun looking at the resources found in these asteroids. Even relatively small metallic asteroids may contain trillions worth of industrial and precious metals like platinum. And bigger asteroids like 16 Psyche could contain enough iron-nickel to cover the world's metal needs for millions of years. At current market prices, the rare raw materials alone would be worth quadrillions of dollars. Well, not really, but technically. For example, there are more than 20 million tons of gold in the ocean's water, worth roughly $750 trillion US. But filtering out the gold would be so expensive that you'd lose money selling it. Right now, asteroid mining has exactly this problem. It's too expensive to replace mining on Earth. Billions of dollars worth of valuable resources in space are worthless if it costs trillions to get them. What makes it so hard? The principles behind mining an asteroid are simple. The basic idea is to choose an asteroid, move it to a place where it's easy to process, and then take it apart to turn into useful products. Unfortunately, all of this collides with fundamental problems humans have yet to solve. Going to space is expensive. It costs thousands of dollars in rocket fuel for each kilogram just to reach a low Earth orbit. Going further out into deep space costs thousands more. We need cheaper space travel to make asteroid mining profitable. One solution is to switch from classical rockets to electric spaceships. We already use electrical rocket engines for many of the space probes on science missions. In principle, we only need to build bigger ones. While electrical engines are not powerful enough to fly to space, they require only a tiny amount of fuel to go very far once they're in space. This means we don't need to spend a lot of money on fuel only to transport fuel into space. This doesn't solve the whole cost problem, but it makes it easier to start our first mission. Now that we have an electric asteroid mining spaceship, we need to find the right asteroid and get it there. We've already successfully visited asteroids with space probes and even collected samples. Still, to make it easier and cheaper, our first targets will probably be near-Earth asteroids. Asteroids that orbit, well, near Earth. After a few months of travel, our spaceship finally arrives at our asteroid. Weirdly formed, littered with small impact craters, it hasn't changed much for billions of years. The first thing that needs to be done is to secure the asteroid and stop it from spinning. There are multiple ways to do this, like vaporizing material with a laser or stopping the rotation with thrusters. Once we have a stable asteroid, we need to wait. Orbital mechanics are complicated, but if you push something in the right direction at exactly the right moment, you can move very big things with very little force. So, we wait for exactly the right moment. Our ship fires its thrusters and nudges the asteroid into a trajectory that takes it near our moon. The moon is useful because we can borrow its gravitational pull to put the asteroid in a stable orbit around Earth, which saves even more fuel. Again, the trip takes months. But all the time since our ship was launched has not been wasted. The first space mining and processing equipment has been installed in orbit and is now carefully moving towards the asteroid. The processor works very differently than on Earth. Giant mirrors focus sunlight and heat up asteroid rock to boil out the gases. Grinders break up the dried rocks into gravel and dust, and centrifuges separate dense from light elements. Even if we only extract 0.01% of the asteroid's mass in precious metals, this is still several times more than you'd get from the same amount of ore on the ground. But what now? How do we get our precious metals safely back to ground? There are a few ways, like loading it into reusable rockets that return to Earth from space. Or if our processor contains 3D printers, we can print a faster and cheaper delivery system. Heat-shielded capsules filled with gas bubbles. These can just be dropped into the oceans where ships tow them away. This could be the starting point of humanity's first real steps towards colonizing the solar system. As our infrastructure and experience grows, our missions get more and more sophisticated. Parts and fuel produced on asteroids don't have to be launched from Earth at all. The first mining operation makes the second one easier, and so on. While the space industry grows and precious materials become cheaper, eventually we could stop mining on Earth. Even the idea of toxic mining down here might become something weird and anachronistic, like having an open fire in your living room. Landscapes ravaged by pollution will heal, while the technological wonders we're used to get cheaper and less toxic to make. None of this is science fiction. We don't need fancy materials or new physics to make asteroid mining happen. We could start building this future today. All we need is an initial push. 3 reasons why we should continue using nuclear energy. 1. Nuclear energy saves lives. In 2013, a study conducted by NASA found that nuclear energy has prevented around 1.8 million deaths. Even if you include the death tolls from Chernobyl and Fukushima, nuclear energy ranks last in death per energy unit produced. While nuclear waste is really toxic, it's usually stored somewhere, while the toxic byproducts of fossil fuels are pumped into the air we breathe every day. So, just by reducing the amount of fossil fuels burned, countless cases of cancer or lung disease and accidents in coal mines have been avoided. If we can choose between lots of dangerous stuff being put into a deep hole and lots of dangerous stuff being pumped into the atmosphere, the former seems more logical. Nuclear energy feels way more dangerous though. Single catastrophic events burn into our memory, while coal and oil kill silently. It's like the death rate of flying versus driving. Even in the best-case scenario, it would take at least 40 years to switch to 100% renewable energy. So for as long as we continue using fossil fuels, nuclear energy will save way more lives than it destroys. 2. Nuclear energy reduces CO2 emissions. Nuclear energy is arguably way less harmful to the environment in terms of climate change than fossil fuels, our main source of energy. Since 1976, about 64 gigatons of greenhouse gas emissions have not been pumped out thanks to nuclear energy. And by the mid-21st century, that could amount to an additional 80 to 240 gigatons. Humanity's energy consumption is rising steadily. According to US government projections, China alone will add the equivalent of a new 600-megawatt coal plant every 10 days for the next 10 years. China already burns 4 billion tons of coal each year. Coal is cheap, relatively abundant, and easy to get to, so it's not likely that humanity will stop using it soon. Nuclear energy might be the only way of dampening the effects of climate change and preventing a catastrophic man-made global warming. Compared to the other things we do, nuclear energy is relatively clean. So even if it is a good idea to quit nuclear energy long-term, it might be a good solution for the next 100 years or so, compared to the alternatives. 3. New technologies. Maybe technology will solve the problem of nuclear waste and dangerous power plants. The nuclear reactors we've used so far are mostly outdated technology because nuclear innovation stopped in the 1970s. There are models like the thorium reactor that could solve the problem altogether. Thorium is abundant, really hard to turn into nuclear weapons, and up to 2 orders of magnitude less wasteful than current nuclear reactors. The waste material might also be only dangerous for a few hundred years, in contrast to a couple of thousand years. 1 ton of thorium is estimated to provide the same amount of energy as 200 tons of uranium or 3.5 million tons of coal. So while we cannot know for sure if alternative nuclear technology will keep its promises, shouldn't we at least do more research before we forego an opportunity to solve lots of humanity's current problems? It might not be an easy challenge, but that hasn't stopped us before. So, should we use nuclear energy? There are risks involved in any great human endeavor, and we have to make an informed decision rather than rely on gut feeling. We've found a new planet, home to octillions of the most extreme beings living in the most absurd and deadly hellscape. In absolute darkness, crushed by the weight of mountains, starved of oxygen, cooked alive, bathed in acid, salt or radiation. And yet, they live for thousands, perhaps millions of years. It turns out, this planet is not in space, it's inside the crust of Earth. This is the deep biosphere, and we basically learned that it exists yesterday. Its volume is at least twice as large as all the Earth's oceans, home to more microbes than the rest of the entire planet. Their total biomass is more than 20 times greater than all humans, livestock and animal wildlife. Let's descend into this mad, deadly world where none of the rules we thought are mandatory for life apply. Going deeper and deeper. Deep life seems to be everywhere we look, below the oceans, near volcanoes, beneath the glaciers of Antarctica, under any landscape we can imagine, and anywhere we live. We'll use a special duck science drill and start our journey in familiar territory, on land, in the soil where plants grow and animals roam. If Earth were an onion, this is the very top of the very top layer. Soil is a lavish four-way partnership of air, water, minerals and organic matter bathed in endless energy. Life lives in luxury here. Plants exploit this paradise and produce more than 30 times the biomass of all of Earth's animals each year, in a constant cycle of growth and decay. Only a tiny fraction of the biomass is buried deeper in the ground, supplying juicy resources for almost 500 million years. As we dig deeper, most of the air has been squeezed out and we cross the water table into a zone saturated with groundwater, rich in minerals and some organic matter. Roots from the most ambitious plants reach down here, and the most common inhabitants are scavengers living off decay. This layer can be pretty cold because it's still slowly warming up from the most recent ice age. We reach bedrock, a foundation of solid rock for all the less solid stuff above, home to fractures filled with water. It can be exposed to the surface or buried hundreds of meters below stuff. Here in the dense bedrock, we're in a weird planet inside the planet, the most thrilling zone of the deep biosphere. As we drill further down, temperatures gradually begin to rise, and soon it gets really hot and the pressure rises. Underneath 400 meters of rock, the pressure is similar to the surface of Venus. We drill faster now, down to 1,000 meters, deeper than the Burj Khalifa is tall. It's about 30 degrees Celsius, and there's almost no free oxygen left. We continue and finally stop almost 4 kilometers down. Above us, pressing solid rock weighing tens of thousands of tons, with pressures as intense as at the bottom of the Mariana Trench. Down here, it's on average 120 degrees Celsius, even hotter if a magma plume is nearby. The heat is a leftover from Earth's formation and from the decay of radioactive elements like thorium and uranium that shower the crust with a constant wave of radioactivity. To make things worse, some rocks are mixed with extreme amounts of salt. Hell. And yet, life is thriving inside rock. If we zoom in, we see that solid rock is not actually solid, it's traversed by cracks, voids and tiny pores. Sandstone, limestone or basalt are so porous that up to 40% of their volume is actually empty space. But even much denser rocks like granite can be split open by cracks and fractures. We've found a gigantic planet-spanning system of microcaves, free real estate filled with water and hardcore microbes, and these caves are moving. Just like the atmosphere is constantly mixing air to create weather, down here rocks are mixing to create rock weather. Submerged mountain ranges are shifting and ripping, crashing and merging. Continents smash into each other with the energy of millions of nuclear weapons, but as slow as your fingernails grow. Countless tiny and not so tiny earthquakes rip open tiny new fissures and passageways, creating new spaces for life and closing others off forever. In this hot, moving pressure cooker, minerals are forged and baked, and organic molecules are created and destroyed. An insane menu for anyone brave enough to try to survive down here. Let's venture into the system of tiny caves and meet some of them. The most extreme living things. We think that octillions of microbes live down here, and naturally they are pretty hardcore. The doomsday preppers of the underworld. Some have big, bulky genomes living entirely on their own, basically forming their own ecosystem, like the bacterium Desulforidus aurex viator. It synthesizes its own food by nibbling carbon or sulfur from the rock and turning it into organic substances. If the conditions get too extreme, or if there's no food around, it kills itself to survive by forming an endospore. It divides into a big and a small part and swallows the small part again, forming a cell within a cell. The outer cell then sheds its water and kills itself, leaving the spore to float around, maybe for thousands of years, until it finds a good place to spring to life again. Others like some company, like the archaea with the clunky name Artiarchium hemiconnexum, that have a rare double membrane covered in weird materials that protect them against the extremes. They shoot out nano-sized grappling hooks to tether themselves and seem to live in cracks and fissures filled with water completely devoid of oxygen, harvest carbon dioxide to create biomass, and may sort of eat hydrogen. The conditions in the deep biosphere are so harsh that other microbes share the hard work by forming consortia. They knit themselves together in a biofilm, a very thin, sticky net that shields them against the extremes. They are miniature cells, often with a small genome, but each good at one thing. One type of microbe eats methane and excretes its electrons. A second type eats these electrons and converts sulfate into sulfite that's then eaten by a third microbe, and so on. Some eat iron, others use electrons to turn nitrogen or carbon dioxide into biomass. Life down here found ways to use stuff that's poisonous to most animals to make food and energy. But still, life is incredibly hard, and resources and energy are super hard to come by. So the most intense strategy for survival down here is to live forever. Like monks who've taken a vow of poverty, deep microbes consume very little and conserve their energy. Their metabolism is up to 1 million times slower than microbes at the surface. They had a meal when you were born and are still digesting it. For most of their life, they exist in a slow limbo. Some even slowly cannibalize themselves, until a sudden influx of resources arrives by pure chance, and then they spring into action and reproduce. With this lifestyle, it seems that extreme microbes can live for centuries, maybe even for millions of years. If they're not hunted to death, of course. Because kilometers deep in limestone habitats, there seem to be spaces big enough for multicellular predators. We've found asexual worms, 100 times longer than microbes, hunting and devouring bacteria. It's not clear if they originated down here or if many earthquakes opened up fractures for water to carry them into the deep. But there are other fierce predators like rotifers or arthropods in the depths, hunting immortal microbes. We wish we could tell you more insane things about life in the deep biosphere, but there's a problem. We don't know that much yet. For one, we can't really get a good look under kilometers of rock. Drilling down could contaminate the samples with microbes from the surface. We've found living ones in deep mines and brought them into the lab, but it's pretty hard to simulate the conditions they feel comfy in boiling hot water, squeezed under mountains, submerged in deadly chemicals, and still see them through a microscope. And the microbes live so slowly for so long that nothing might happen. A lot of what we know about them we got from turning them into a slurry and looking at what their genes could do, like breathing nitrogen or eating methane. We know that the diversity of life in the deep biosphere must be staggering, and that some of the most hardcore and extreme beings live down there. This is a proper frontier of science, super hard to study, and most of what we know we've learned in just the last 20 years. There is so much more undiscovered mystery for us that could bring us progress in medicine, energy, the climate, and more. Let's end by moving our gaze from the inside to the outside again. Since we now know how extremely large the deep biosphere is and how life down there survives without light, oxygen, sane temperatures, or not being covered in poison, could there be deep biospheres all over the universe? Maybe all you need is a planet or moon with internal heat or radiation, and a chemical composition that allows microbes to build the parts they need. Some scientists suggest there could be 10 of them in the solar system, hiding beneath a seemingly dead and frozen surface. So as we learn more and more about the life below our feet, we may accidentally learn about life in the universe. Our first ever PC game, Starbirds, is out now in early access. Find out more at the end of this video. Imagine, a stadium-sized asteroid is going to hit Earth in 2 weeks. Even at this moderate size, a fireball brighter than the sun tears through the atmosphere at 60 times the speed of sound, and the destructive power of 4,000 Hiroshima bombs flattens cities, killing millions. This isn't science fiction. Many killer asteroids were only spotted at the last moment. In 2019, asteroid OK, as big as a 30-story building, was discovered just 1 day before it grazed Earth closer than some of our satellites. Last year, the even larger asteroid MK was spotted 13 days before it passed us closer than the Moon. If they'd have hit Earth, they would have unleashed the destructive power of 3,000 and 9,000 Hiroshima bombs. Stunningly enough, humanity doesn't really have a plan for this. Scientists have devised all kinds of tricks to push dangerous asteroids away, painting it so sunlight will deflect it, landing thrusters to steer it, scorching it with lasers, or even crashing spacecraft into it. But they all have a big problem. They're the equivalent of trying to deflect a cargo ship by throwing a bag of potatoes at it. They do move the asteroid, but only by a tiny bit. With these methods, you need to act years or even decades in advance to make an asteroid miss the Earth. But very recently, scientists have developed a new, spectacular way to destroy killer asteroids that we could implement with today's technology. Let's see how this works with our 100-meter asteroid heading for Earth. the secret weakness of asteroids. For a long time, people imagined asteroids as being gigantic stones made of rock and metal. But it turns out most of them aren't like that. They're more like bags of loosely packed gravel, heaps of pebbles, precious minerals and dust barely held together, which means that instead of just nudging them, we can do something better: pulverize them. And the obvious choice is, of course, a nuke. So let's go. We load up a nuclear warhead, launch, aim at our deadly asteroid and... Oh, the asteroid destroyed the nuke. Asteroids can approach Earth at 70,000 kilometers an hour, enough to cross the Atlantic in 5 minutes. No bomb we've ever made could survive such an impact. So if we go for a head-on collision, the asteroid will wreck the nuke before it even has a chance to explode. Okay, easy. Let's explode the bomb before it touches the asteroid. Scientists have estimated the optimal distance, which for our 100-meter killer friend would be a few tens of meters above the surface. Launch, set the timer, and... The explosion has made a dramatic crater and nothing else. Unfortunately, in space there's no air to carry a shockwave, so most of the explosion's energy is lost. The rock will still hit us in 2 weeks, only a few kilometers to the left. Striking such a behemoth with a nuke is like hitting our cargo ship with a washing machine instead of potatoes. Better, but still useless. Okay, let's go the movie route. Land someone on the asteroid, drill a hole, and bury a nuke inside to avoid all of these problems. And indeed, this is possible in theory, albeit suicidal in practice. Landing on any space body is a nightmare. Even on fairly big Mars, whose surface we know almost perfectly, roughly 70% of our attempts have failed. So imagine the chances of landing a crew and a nuclear bomb on a small and extremely fast asteroid discovered just 2 weeks in advance. Even if we succeeded, drilling in microgravity is painfully slow since there's no downward pull to help you. So we'd need an agonizing amount of time that we don't have. So sadly, that's not the answer. We have to think less like Hollywood and more like a lumberjack. The smart way. If you want to split a log, you don't hit it with a rock. You use an axe, a dense and perfectly shaped tool designed to break things apart. And just in the same way, scientists have found a new tool to destroy asteroids: super dense, ultra-fast cosmic bullets. We won't even have to shoot them. Our cosmic bullets are called penetrators. A few meters long, slim and made of tungsten, a metal way denser and harder than rock. They work in an extremely simple way. You just put the penetrators in the way of the asteroid to float silently in space. From the perspective of the asteroid, you wouldn't see a few tiny bullets sitting still. You'd see them rushing at you at 70,000 kilometers an hour. It doesn't matter who stands still and who's fast. But this speed means that by far the longest part of this mission is to get to the asteroid in time. We can't destroy it too close to Earth because its fragments will slam into the atmosphere all at once with the power of thousands of nuclear bombs. Our atmosphere can absorb isolated chunks, but if thousands of them strike together, their shock waves will add up and kill millions. So instead, we need to get it 1 day before impact, when the asteroid will be nearly 2 million kilometers away, more than 4 times further than the Moon. A vast distance, but doable. Our current rockets can cover this in about a week. We'll just send one penetrator about 2 meters long and weighing 2.5 tons. Once our rocket arrives, it puts the penetrator in place to cause maximum damage, and then we wait. A tiny speck of light appears in the vast distance, and then suddenly it's here, shooting at us faster than the speed of sound. We'll slow down time to see exactly what happens. The asteroid crashes into the penetrator so fast and with so much violence that the power of 120 metric tons of TNT is released into the asteroid. The rock vaporizes and the tungsten melts away, carving a wound that tunnels through the asteroid. The damage is too much, and with all of this energy looking for a place to go, the asteroid is blasted into thousands of pieces. The debris spreads out into a diffuse cloud. A day later, the fragments hit Earth, dispersed over hundreds of thousands of square kilometers and turning an apocalypse into a mostly harmless show of cosmic fireworks. So if we prepare and get everything ready, spotting a killer asteroid with 2 weeks' notice would be enough. But this was just a small asteroid. What if we face a cosmic mountain, a planet killer carrying the destructive power of tens of thousands of nuclear arsenals. The non-avian dinosaurs would tell you about it, but they're dead. What if it is a planet killer? Planet killers are objects so vast and powerful that they would end most life on Earth in a single strike. The most dangerous ones are comets from the outer fringes of the solar system, so distant and dark that tracking them is impossible. Comets are dirty ice balls the size of mountains, more fragile than pure rock, but also much faster and violent, traveling at around 140,000 kilometers per hour. In 2020, the comet Neowise, with the power of 6,000 times all the nuclear bombs on Earth, was discovered just 4 months before its closest approach to Earth. What if we find such a beast 6 months before it's going to crash into us? Do we have a chance of surviving this? Unfortunately, this would be extremely hard for a bunch of reasons. First of all, our planet killer comet has so much more mass than a tiny killer asteroid that simply breaking it into millions of pieces would not help us that much. The chunks that hit Earth would still be massive and numerous enough to set the sky ablaze and kill most life on Earth. So we need to make most, if not all of its fragments completely miss Earth. But to do that, we need to destroy it much further away, as far away as Mars. And to destroy a mountain, we need way more penetrators. Hundreds of thousands. And this is, well, a huge problem. To travel this far and to transport this much payload, we need at least 24,000 super heavy rockets. As of today, humanity has 2, and they're not really finished yet. Even if all the industries in the world do nothing but switch to building rockets, we wouldn't finish in time. If we actually discovered a planet killer today, there's literally nothing we could do about it. Except, maybe if we combine penetrators with a bit of Hollywood and our old friend the nuclear bomb, there is still a way. For this plan to work, we basically need to have all the parts ready beforehand. A rocket like NASA's SLS, the one planned to take astronauts to the moon, loaded up with everything we need, ready to launch. As soon as the planet killer is spotted on its way to wipe us out, we launch a single rocket to meet it. For 5 long months, it travels through the nothingness of space as life on Earth nervously continues. Finally, it reaches its destination a bit beyond the orbit of Mars. Now, we deploy 5 massive penetrators in sequence, one perfectly lined up 2 kilometers after the other. The engineering challenge of aligning and timing this correctly is horrendous, and we only have one attempt. So, a few very brave astronauts go on this one-way trip to supervise the process with no way home. Nervous hours pass as all of humanity watches the skies and screens. And then the moment comes. The icy mountain of death appears in full, and then it's already here. Slow down time again. The comet smashes into the first penetrator at 140,000 kilometers an hour, unleashing the power of 2,000 tons of TNT. Ice, rock, and tungsten liquefy in an instant as the energy of the impact eats itself dozens of meters deep into the mountain. Here's the second one, perfectly hitting the same spot, punching directly into the crater, smashing, melting, drilling. The third and fourth penetrators repeat the process again, now smashing a tunnel about 100 meters deep. But this time, this is just a scratch on the surface of the monster. The comet is not really damaged yet. And then comes the final penetrator and its toxic load. 300 megatons in nuclear warheads, 20,000 times more energy than the bomb that destroyed Hiroshima. It travels deep into the tunnel, and just before it hits the end, it explodes. This time, the nuke works. Instead of hitting nothing in the vacuum, the energy of the explosion smashes into rock and gravel and ice. On top of vaporizing it from the inside, there's so much shock and push and punch that a frozen world billions of years old dies from within, turning into a cloud of millions of fragments spreading in all directions. Humanity is saved. To make this happen in reality would take unprecedented planning and precision, and yet it's possible. Not in a century with sci-fi technology, just with the rockets, engineering and knowledge we already have today. Climate change is just too much. There's never any good news. Only graphs that get more and more red and angry. Almost every year breaks some horrible record, from the harshest heat waves to the most rapid glacier melt. It's endless and relentless. We've known for decades that rapid climate change is being caused by the release of greenhouse gases. But instead of reducing them, in 2019 the world was emitting 50% more CO2 than in the year 2000. And emissions are still rising. Why is that? Why is it so hard to just stop emitting these gases? Our collective CO2 emissions can be expressed as a product of 4 factors and their relationship with each other. 2 of them explain why worldwide CO2 emissions are still rising, and 2 explain how we can stop that. Population size, economic growth, energy intensity, and emissions per energy unit produced. Number 1. Population size. People need food, homes, and clothing, and they demand luxury products from iPhones to $1 cheeseburgers. More people, higher CO2 emissions. It's a very simple equation. The global population is growing, and according to the UN, it will level off at about 11 billion in 2100, which is 40% more than today. The only way to slow down this growth is investment in healthcare and access to contraception and education in developing countries. But even with massive investment, it will take a few decades for the effects of lower birth rates to manifest themselves. So the global population will keep growing for the foreseeable future, and as a consequence, global CO2 emissions will rise over the next few decades. Number 2, growth or getting richer. But it's not just about our numbers. The richer and more developed we are, the more emissions our lifestyle produces. A programmer in the US has a higher CO2 footprint than 50 farmers in Uganda. The world's wealth is growing almost everywhere. And although it's far from evenly distributed, economic growth has led to the highest standards of living and the largest reduction in extreme poverty in human history. Growth has become the dominant mantra of the world's economies, no matter what kind of political system they have. It's unlikely that rich countries will give up the concept of growth anytime soon. But even if they were to, developing countries want to become rich too. For billions of people, the end of growth would probably mean staying poor, and so developing countries are not willing to stop growing their economies. All in all, we can be sure that growth as a guiding economic ideology is not going to go away anytime soon. More countries and their citizens around the world will grow and become richer, while the rich economies will continue to grow their wealth. There are some signs that growth can be decoupled from CO2 emissions, but we're not close to that yet. As a consequence of this growth, CO2 emissions will rise. Okay, so far we've learned that because of population growth and economic growth, humanity's CO2 emissions will increase, which is the opposite of what should be happening. We need to slow, peak, and then reduce annual emissions. The next 2 factors describe how we can actually do this. Number 3, energy intensity. Energy intensity describes how efficiently we use energy. A street food vendor in rural Brazil might burn coal to cook, while a street food vendor in France might use an induction stove powered by nuclear energy. The latter is way more efficient. The more efficient something is, the less energy we need to do something, be it powering a metropolitan area or grilling a kebab. So making our technology more efficient and coming up with more efficient ways to organize our societies is one of the most important ways to reduce the modern world's CO2 dependency. This can mean everything from reducing power consumption with AI, the electrification of the transportation and industrial sectors, or sustainable concrete production. The opportunities for improvement are almost limitless, and human ingenuity can run wild. But we know that increasing efficiency alone will not be enough, mostly for 3 reasons. 1. Direct rebound effects. This means that once something becomes more efficient, it's used more, and so overall the increased efficiency does not lead to a reduction as impressive as you would first think. Or worse, sometimes more efficiency makes humans not use less of a resource, but more of it. When planes became more fuel efficient, ticket prices decreased and more people started to travel by plane. So making things more efficient does not automatically mean less energy use in total. it might have the opposite effect. 2. Indirect rebound effects. Sometimes when you save money on a thing that's become more efficient, you might spend it elsewhere. For example, if you buy a more fuel-efficient car, you save money on fuel and end up with extra funds in your bank account that you might spend on a vacation and take a flight with. So, in the end, you might actually emit more CO2 despite getting a more efficient car. 3. And lastly, the more you optimize for efficiency, the harder and more expensive it becomes to get more efficient. So over time, the return on investment slows down. And with many technologies, we are already pretty efficient. But regardless of how efficient we make our economies, as long as we need at least some energy, we will have emissions. Efficiency alone won't create a zero-carbon world. This brings us to our last factor. Number 4. CO2 emissions per energy unit used, or our global carbon footprint. Humanity's global carbon footprint is the CO2 released per energy unit generated. For example, coal plants release much more CO2 than solar power per unit of energy. This relationship is crystal clear. The more fossil fuels we burn, the higher our CO2 output. Fossil fuels are the greatest lever humanity has right now. Of course, it's impossible to shut down coal and oil overnight without throwing society into chaos. But the reality is that we're not doing nearly enough to keep fossil fuels in the ground and use lower carbon alternatives. We need to do 2 things to speed the transition away from fossil fuels. First, we need to use the real leverage we have today with today's technology. There are a lot of things we can do extremely quickly. We can leave nuclear power plants online longer. We can cut subsidies to the fossil fuel industry and funnel them into renewables. We can price carbon emissions harshly and increase the price each year to create strong incentives for the world's industries to transition. We can enforce strict standards for energy efficiency and for any type of new construction. We can phase out fossil fuel vehicles. Next, we also need to invent new and better technology. Without new technologies and innovation, it will be impossible to achieve a zero CO2 emission world, be it from technologies like carbon capture or a new generation of nuclear power plants to new batteries that revolutionize the energy storage from renewables. But innovation takes time, years and decades, and we don't have this time. Every year we keep adding more carbon to the atmosphere. This means we can't keep relying on innovation alone. We need to find ways to reduce emissions today while we invent what we will need in the future. The less fossil fuel we burn over the next few years, the more time we give innovation to catch up. The more low-carbon energy infrastructure we build today, the more we can compensate for economic growth and the people born today. The more coal power plants in construction we stop from being finished, the more CO2 we save. Neither innovation nor the alternatives we're using today alone can solve rapid climate change. But innovation, together with a decisive move away from fossil fuels where it's possible today, could do it. Solving climate change will be complicated. We have to account for the needs of billions of people and the reality that right now, society runs mostly on fossil fuels. This will not change overnight, but it needs to change as quickly as possible. And it is still very much possible. Today, we are answering an age-old, very scientific and important question. What if the moon crashes into Earth? It's more interesting and weird than you probably think. Let's start with the basics. Why isn't the moon on its way to crash into us already? We know that Earth's gravity pulls everything towards it, including the moon, but somehow it stays up, as if suspended by some opposite force. But there is no other force countering gravity. Instead, the trick to staying up is a sideways motion that we call an orbit. You see orbits every day. When you throw a ball, it makes a tiny little orbit. The only difference between the ball's orbit and the moon's is that the ball eventually hits the ground. Basically, the reason is speed. If you could throw your ball fast enough, it would bend around the world and come back to you. If there were no air slowing it down, it could orbit forever. And this is what the moon does. falling sideways around Earth very fast with no air slowing it down, orbiting Earth every 27 days at 3,600 kilometers an hour. So, for the Moon to just stop in its orbit and plummet to the Earth would break more laws of physics than we have time to explain. So, how do we crash it into Earth? In a nutshell, to change an object's orbit, you need to change its speed, which changes where gravity takes it. But even small changes require enormous forces, which is why all the large objects in the solar system are so stable nowadays. According to science, the Moon is big and very massive. Even igniting billions of rocket engines all over its surface would barely move the Moon. It looks like nothing short of magic will make the Moon fall, so we'll use a magic spell that slows down the Moon so much that it changes its orbit and spirals towards Earth. To get the most from the experience, the Moon will take exactly 1 year before it hits Earth. Ready? 3, 2, 1. Magic. Month 1. For the first few days, nothing really changes. The Moon gets a tiny bit brighter and scientists get confused, but the rest of us don't notice anything different. The only noticeable real effect of the Moon on the Earth are the tides. Tides exist because while Earth pulls on the Moon's gravity pulls back on the Earth. Since the strength of gravity gets weaker with distance, different parts of the Earth feel a slightly different pull, which causes the Earth, especially the oceans, to bulge when the Moon is above them and contract a little on the sides when it's not. As Earth rotates every day underneath the Moon's influence fluctuates, causing the water level of the oceans to rise and fall by about half a meter twice a day. But with the Moon drawing ever closer, high tide gets higher every day. At first barely noticeable, within a month the Moon has covered half the distance to the Earth and ocean tides have grown to 4 meters. Every day high tide comes and waves flood coastal cities. And there's no end in sight. With the Moon drawing ever closer, tides rise ever higher, inundating another city and more inhabited land with salty water every day. Month 2. By the end of month 2, the Moon has covered 2/3 of the distance to Earth and global infrastructure is crumbling as tides rise above 10 meters, displacing up to 1 billion people who happen to live near the coastlines. As ports become inoperable, shipping grinds to a halt. Not only will it slow down the delivery of Kurzgesagt products, but also less exciting things like food. Global communications fall into disarray. 95% of the internet is carried by ocean-crossing cables, and while these largely don't mind the water, their terminals on land do. Living inland doesn't guarantee safety either. Tidal bores cause rivers to flow backwards, carrying salt water to contaminate surface and groundwater supplies. Gas shortages follow as all refineries near the coast are abandoned. Countries are left with the supplies they had on their shelves, and strict rationing will begin. In the cities, chaos reigns during the scavenging hours of low tide, while survivors take refuge in high-rises when the water returns. Month 3. 3 months in and the Moon is close enough to disrupt communication and navigation satellites. While it's normally far too distant for its gravity to cause any major problems for our satellites, the closer it gets, the more warped their orbits become. As their fuel for orbital corrections runs out, satellites careen out of control. Months 4 and 5. On Earth, the tides are rapidly growing to about 30 meters and will be reaching 100 meters in height in a few short weeks. At low tide, the ocean recedes hundreds of kilometers, exposing the continental shelf like vast deserts, while at high tide, walls of water drown agriculture, houses, and skyscrapers. And now, almost 5 months in, the apocalypse has finished its warm-up act. Since the oceans are on average only 3 kilometers deep, the tides have reached their maximum. Up until now, the water in the oceans could flow, absorbing most of the Moon's gravitational squeezing, but now the Earth itself is really feeling the squeeze of the ever-approaching Moon. These aren't so much tides of water, but tides of rock. The squeezing of the planet, combined with the weight of quintillions of tons of water sloshing on and off the tectonic plates, creates enormous stresses below and begins to cause earthquakes of increasing magnitude and intensity. It's impossible to say how serious these earthquakes might be or where they occur, but like a child jumping on their bed until it breaks, no good can come of it. Strong tidal forces lead to volcanism on other planets and moons. On Earth, squeezing the planet disrupts the magma reservoirs inside the crust, triggering sizable, climate-altering eruptions in Chile, New Zealand, Yellowstone, and elsewhere. Meanwhile, watching patiently above is the Moon. Still no bigger in the sky than a small cloud. Within 75,000 kilometers of Earth, it is bright enough to illuminate the night sky like twilight. Months 6 and 7. After half a year, the Moon is entering the space once occupied by geosynchronous satellites, where it orbits Earth every 24 hours. It appears to float at one spot in the sky, unmoving, cycling through a full set of phases every day, but only visible to half the planet. With the Moon stationary above the Earth, the tides seem to freeze in place. Half the world flooded, half with its water seemingly returned to the sea, as if Earth is holding its breath to prepare for the worst. As the Moon sinks further, you might wonder if its gravity would overpower Earth's, pulling you up and ending your misery. Fortunately not. The Earth's surface gravity is about 6 times stronger than the Moon's, so even if the Moon were hovering right on top of you, you would still stay on the ground. On the Moon, things are different though. The near side of the Moon is more strongly affected by Earth's gravity, so during the next few months, it starts to stretch forward towards the Earth into something of an egg, triggering deep moonquakes as the lunar rock flexes and changes shape. Though barely noticeable now, this squish will grow to hundreds of kilometers in a matter of months. Months 8 to 11. At this point, the apocalypse has arrived, and we can summarize the months before the crash as everybody left has a really bad time. The tides sweeping over the Earth slow down and then reverse their direction because the Moon now orbits Earth faster than it rotates. The planet will experience an abundance of earthquakes and volcanism. Massive amounts of volcanic aerosols rise high into the stratosphere, shiny enough to reflect sunlight back into space. What little light gets through is rust red and is periodically diminished by daily eclipses. The result is a rapid global cooling with acid rains and summer snows killing even the hardiest plants. The clock runs out on civilization. Billions have perished while an X-shaped moon is still drawing closer. Let's get ready for the grand finale. Month 12. Finally, at the end of the year, the Moon has reached the Roche limit. That's the point where Earth's gravitational pull on the Moon is stronger than the Moon's own gravity. Things on the lunar surface start falling towards Earth, and by the time it crosses 10,000 kilometers, the entire Moon disintegrates into rubble, smearing itself into a massive ring system around the Earth. Fortunately, the Moon's disintegration means the misery on Earth has ended. No Moon means the general apocalyptic nature of things comes to a halt. The oceans recede, flowing off the land one last time. Any survivors are treated to a view of tremendous arches spanning the sky, glimmering in the sunlight, illuminating the night sky more brilliantly than any full moon ever could, while meteor showers of moon dust fill the sky. It's hard to say what happens next, but the tranquility may be short-lived. If too much moon dust rains down, friction heats the atmosphere, possibly boiling the oceans. If not, the enormous shadows cast by the rings, combined with all the volcanic and meteoric aerosols, block even more sunlight, and a period of runaway cooling could begin that freezes much of Earth's surface solid. In any case, at some point people will emerge again, from submarines or bunkers or mountaintops. They will not have a great time before rebuilding civilization, and their success is not guaranteed, but at least they'll be trying to do so with beautiful rings in the sky. Our home is burning. Rapid climate change is destabilizing our world. It seems our emissions will not fall quickly enough to avoid runaway warming, and we may soon hit tipping points that will lead to the collapse of ecosystems and our civilization. While scientists, activists, and much of the younger generation urge action, it appears most politicians are not committed to doing anything meaningful, while the fossil fuel industry still works actively against change. It seems humanity can't overcome its greed and obsession with short-term profit and personal gain to save itself. And so for many, the future looks grim and hopeless. Young people feel particularly anxious and depressed. Instead of looking ahead to a lifetime of opportunity, they wonder if they will even have a future or if they should bring kids into this world. It's an age of doom and hopelessness, and giving up seems the only sensible thing to do. But that's not true. You are not doomed. Humanity is not doomed. Despite the seriousness of the situation, for years positive trends have accumulated, and there is finally some good news and a clear path towards our collective climate goals. Welcome to our TED Talk. Please watch this video to the end. Check out our detailed sources afterwards to learn more. Okay, let's start with the scariest things. Cancelling the apocalypse. Some of the most widely shared stories about climate change are that it is an existential threat, the end of human civilization, and maybe even our own extinction event, and that it's basically unavoidable now. But what does science actually say? As of 2022, the global average temperature has risen 1.2 degrees Celsius compared to pre-industrial times. Limiting warming to 1.5 degrees was the most ambitious goal of the Paris Agreement, but we are not likely to meet it. Already with the warming we have today, hot places will get hotter, wet places wetter, and the risk and strength of extreme weather events increase significantly. Warming beyond 2 degrees makes all of these extremes more extreme. Extreme weather events more common, with more ecosystems under major pressure. Some will not survive. At 3 degrees, significant parts of Earth, especially in developing countries, might become unable to feed their populations. Heat waves will become a major global issue. Large-scale natural systems will break down. The scale and frequency of hurricanes, fires, and droughts will further increase and cause trillions in damage. Poor regions and subsistence farmers will be hit the hardest. Hundreds of millions of people will need to leave their homes. In the 4 to 8 degree range, the apocalypse begins. The hothouse Earth, where things change so quickly that it may become unable to support our large human population and billions may perish, leaving the rest on a hostile alien planet. A decade ago, for lack of action and perspective, many scientists assumed a 4+ degree world was our future, and a lot of public communication focused on exactly this future path. Luckily, it's much less likely that this version of the apocalypse will come to pass. If current climate policies stagnate, we're likely to end up with warming of around 3 degrees Celsius by 2100, which is scary and tragic and far from acceptable. But this is actually good news. How? In the last decade, we've seen enough progress that most scientists now think that we have likely avoided apocalyptic climate change. Although substantial risk still remains, we can pretty confidently say that humanity isn't going anywhere. Civilization might have to change, but it will endure. Which begs the question, what has changed over the last 10 years, and is this really good news? The invisible shift. You probably know this story. The last decade has been an immense failure for climate policies around the world. Instead of passing comprehensive, binding bills that would meaningfully reduce emissions, we mostly did nothing. A lost decade with one negative record after another. And this story is true, and it's one reason why so many people are giving up. But it is not the whole picture. Despite the lack of climate policies and ongoing lobbying and misinformation campaigns from the fossil fuel industries, there was a lot of progress. Let's go back 20 years to see why today is so different. Between 2000 and 2010, greenhouse gas emissions had grown by 24%, 3 times as much as the increase in the previous decade. Subsidies for fossil fuels aimed at promoting economic growth caused a colossal increase in their consumption. For developing countries like China and India, coal was the cheapest fuel for growth, while rich countries showed little interest in changing their ways. In 2010, many people expected these trends to continue. Instead of decreasing fossil fuel use, its consumption would rise. The next decade turned out to be very different though. First of all, coal burning in developing countries like India has slowed down or leveled off like in China, and it's plummeted in rich countries like the UK and US. Since 2015, 3/4 of planned coal plants have been cancelled and 44 countries have committed to stop building them. 10 years ago, that would have seemed like wishful thinking, but today we can say with confidence, coal is dying. It's just not competitive anymore. Because technologies we thought would remain expensive matured rapidly instead. Renewable electricity has shown explosive progress. In a mere decade, wind energy got 3 times cheaper. Solar electricity is now 10 times cheaper. Cheaper than coal or any other fossil fuel burning power plant, despite the massive subsidies and global infrastructure propping up fossil fuels. 25 times more solar and nearly 5 times more wind electricity is produced today compared with 10 years ago, which is of course not nearly enough. One of the biggest obstacles is the variability of their power output. Renewables need a lot of energy storage to be a reliable power source, like expensive batteries. Amazingly, battery prices have decreased by 97% in the past 30 years, 60% in the last decade alone, which will serve all kinds of green technology like electric cars. You might say, well, that's great, but didn't Kurzgesagt's last climate video say that while wind and solar are nice, we need nothing less than a fundamental transition of our global industrial system? Yes, but luckily the shift goes beyond just the energy sector. Throughout the economy, people are working on improving current technology to lower emissions. We're rapidly replacing old incandescent light bulbs with LEDs that are 10 times more efficient. In 2020, about 7 out of 10 new cars in Norway were electric or hybrid. In 2021, it was already 8 out of 10. And the list goes on, from electric heating and better insulation to ships traveling at half speed to save fuel. Wherever you look, you find scientists, engineers, and entrepreneurs trying to solve some aspect of climate change. Enormous amounts of human ingenuity are being brought to bear on this problem, with more and more people deciding to prioritize preventing rapid climate change. Solutions for low-carbon production of cement, electronics, and steel, and innovations like artificial meat and carbon capture are in the works. The more of these technologies we deploy, the cheaper new and better technology gets. The cheaper they get, the more people use them, and so on. We can see the impact already. The domestic CO2 output of rich countries is falling without a major recession. Since the year 2000, the EU as a whole shows a 21% decrease, Italy 28%, the UK 35%, Denmark 43%. But the best news may be that emissions are no longer necessarily coupled with the economic growth. In the past, this was an inconvenient truth. To get richer, you had to emit more, which led to fierce arguments between developing and developed countries about the fairness of reducing emissions while their populations were still poor. But in the last decade, we've seen that it is possible to increase prosperity without increasing emissions. Emissions in the Czech Republic dropped 13%, while their GDP grew by 27%. France reduced their CO2 emissions by 14%, while increasing GDP by 15%. Romania saw an 8% decrease and 35% growth. And even the largest economy on Earth, the USA, decreased emissions by 4% while growing their GDP by 26%. Some of you may call this a numbers trick, that rich countries are just exporting emissions to poorer nations by moving the dirty parts of their economies like manufacturing. But even when we account for all of our imported goods, the numbers still look positive. It's no longer a matter of having to choose between prosperity and the climate, as it seemed to be a decade ago. Developing countries will profit from that because as rich countries pay for the expensive development of green technologies, they can adopt them more cheaply. They can skip most of the high emission phase that today's rich countries went through. We are at the point where not decarbonizing is a bad business decision. And we haven't even really talked about solutions like carbon capture. In 2000, it didn't really exist. In 2022, that technology does exist and costs around $600 to remove 1 ton of CO2 from the atmosphere. As investment pours in and the technology matures and begins to scale, it's likely that these costs will plummet over the next few decades. So everything's fine then? Well, let's not get carried away. All of these processes are great, but not nearly fast enough. We're still doing way too little, and technology will not magically solve everything. We need to use fewer resources and use them longer, design consumer goods that are repairable and durable, and decrease our energy requirements. We need much better infrastructure, agriculture, and cities. It will still be hard work, especially to get the right policies passed and enacted. But for the first time ever, there are a few trend lines pointing solidly in the right direction. And now imagine if all of this was achieved without proper financial and political support, and despite fossil fuel lobbying. Just think what humanity can do when climate change finally gets the political attention and funding it needs. So is it okay to feel hopeful again? The situation is still dire and serious, so what's the point of focusing on this side of the story? The trap of hopelessness. Climate change can feel overwhelming and make your future seem bleak. The sadness and hopelessness that many people feel is real and very destructive because it causes apathy. Apathy that is only serving the fossil fuel industry that is still delaying change however it can. In a sense, they have weaponized hopelessness. We are now in Phase 4 in the public debate about rapid climate change action. Phase 1 was, climate change is not real. Phase 2 was, climate change is real, but not caused by humans. Phase 3 was, climate change may be caused by humans, but it's not that bad. Phase 4 is, climate change is no longer avoidable. We are doomed, and it doesn't matter what we do. If we want the world to change, we first need to believe that change is possible, and we have an abundance of evidence that it is. Changes to our industrial system are gaining momentum, technology gets better and cheaper, climate change has become a key issue in most free elections. As more and more younger people move into influential positions, they prioritize climate change and work on new solutions. In 2022, most governments not only acknowledge it, but set their own net zero goals in democratic and autocratic countries. The results of years of fighting a steep uphill battle are now clearly visible. The pressure needs to keep increasing to make sure that the promises made today are actually kept. Climate doomerism is the equivalent of giving up, even though you can still prevent not just the worst case, but also mitigate most of the bad things, make changes in time to adapt better, and prevent the poorest from suffering. That is why hopelessness and apathy are so dangerous. If the last, in many ways, wasted decade has shown anything, then it's that progress is being made, and that dire scenarios are just predictions, not our sealed fate. As of 2022, based on current global policies, we will end up in a 3 degrees world. Now it's our job to yet again prove the predictions wrong, despite how serious and urgent things are. To turn that 3 degrees into a 2 degrees and then see where we can go from there. For that, we need hope. And we hope we gave you that today, at least a little. That you feel that things are serious, but also that you have a future. That you can have kids without dooming them or the world. That taking action today is worth it. And that despite powerful industries doing everything to delay it, society is changing. If you need a more concrete roadmap of what you can do personally, we're working on a follow-up video to talk about that in greater detail. Doomerism, inactivity, and weaponized hopelessness are the only trump cards left for the powers that don't want change. Don't let them win. Do we need nuclear energy to stop climate change? More and more voices from science, environmental activists, and the press have been saying so in recent years. But this comes as a shock to those who are fighting against nuclear energy and the problems that come with it. So, who's right? Well, it's complicated. To slow rapid climate change, the world needs to reduce greenhouse gas emissions to net zero. In 2018, 3/4 of global emissions were released through energy production, namely by burning fossil fuels. Energy is a broad term that describes all sorts of stuff, from moving things and people around to putting things big and small together or heating our homes. Currently, 84% of the world's primary energy comes from fossil fuels, 33% from oil, 27% from coal, and 24% from gas. Around 10% of the global oil supply is just used to burn in boilers to make our homes cozy and warm. Only about 16% of global energy is from low-emission sources, almost 7% from hydroelectric, 5% from solar, wind, bioenergy, wave, tidal, and geothermal combined, and about 4% from nuclear. So we pretty much rely on coal, oil, and gas to keep our civilization going, which means it's actually very hard to transition away from them. To have a chance of escaping fossil fuels without throwing humanity back into the Stone Age, one of the most impactful things we can do is to electrify as many sectors as possible. Electricity is the stuff that appears like magic when you plug something into a socket so you can watch YouTube. Every industry that can switch from burning fossil fuels to electricity needs to do so, from electric cars to electric heaters. Why do we need to bet so hard on electricity? Because we can produce electricity with low-emission technologies like solar, wind, or nuclear. So electricity is a real lever for a radical transition. But there are a few problems making this transition really hard. First of all, in most places in the world, electricity is still generated mostly by burning fossil fuels. And not only that, in the last 20 years, the world's electricity usage increased 73% in absolute terms. While we are installing renewables at record speeds, at the same time, the amount of fossil fuel we're burning for electricity still keeps rising year by year. Renewables have so far not been able to catch up with the demand for new electricity, and so despite our progress, emissions from electricity are still rising worldwide. The other alternative to fossil fuels is nuclear, and even though it's not renewable, its greenhouse gas emissions are tiny compared to burning stuff. But in the last 20 years, nuclear has basically stagnated. Countries like China, India, and South Korea built new reactors, while Germany and Japan have been actively taking their nuclear plants offline. Which seems a bit weird if we look at the countries with the most low-carbon electricity in the world that get most of their juice mainly from two sources, nuclear or hydropower. Take France and Sweden. In France, only around 10% comes from fossil fuels, while 67% comes from nuclear and 23% from renewables, primarily hydro. In Sweden, almost 30% comes from nuclear power and about 45% from hydro. So we know that nuclear energy can work at scale. On the technical side, because of the lack of investment and innovation in the last few decades, the majority of the world's nuclear reactors are pretty old technology that's very costly to replace. In most Western countries, building nuclear reactors has become very expensive for a variety of reasons, like a loss of know-how in constructing them, policy changes, and increased regulatory constraints, so it can take a decade or longer just to finish a power plant. In contrast, countries like South Korea, China, India, and Russia are able to build new nuclear reactors comparatively quickly and at a competitive cost. Still, generally in the West, the current generation of nuclear power plants are more expensive to build and maintain than most fossil fuel alternatives. There are also the concerns about nuclear waste and the fear of accidents, but we cover those in other videos in more detail. We have designs for nuclear reactors that solve many of their problems, namely small reactors that take less time and money to get started. There are also next-generation technologies that can already turn radioactive waste into new fuel, but so far these have not been deployed at a scale where they can have a significant impact on the nuclear sector. Considering these uncertainties, some argue that nuclear power is a dangerous relic of the past and that we should just let it go and focus on renewables. But while renewables undoubtedly are the future of electricity, they still have their own huge challenges to overcome before they can take over the vast majority of the electricity grid. The main problem is reliability and consistency. It's not always windy, and the sun doesn't always shine, especially in the mornings and evenings when humans need the most electricity. The variations between seasons don't make this issue easier. To make renewables reliable and not risk blackouts, we need massive storage capacities where we can save energy collected when the sun or wind are at their peak and release it later when we actually need it. Until this is possible, other sources of electricity need to provide a controllable load that creates the reliability of supply that our civilization needs to run properly. Eventually, we will be able to do this with renewables, but we need a lot of batteries or storage power plants. Right now, we simply don't have the tech and the capacities to make this transition fast enough to replace fossil fuels. But even if we could, there's another aspect we have to take into account. We're not just trying to kick fossil fuels out of electricity, we're trying to replace energy with electricity. If we're going to electrify sectors that currently use fossil fuels, like cars or heating, we will need significantly more electricity than we're currently using everywhere around the world. And if the electricity needs of the world population continue to grow as they have over the last 20 years, we'll need even more. It all comes down to one thing. No energy source is perfect. All have their own unique problems. Both renewables and nuclear energy require time, investment, and technological innovation. On their own, neither is ready to remove fossil fuels from our electricity grid, although activists on both sides claim that they are. In the end, the question is how we want to deal with all these challenges. Should we give up nuclear immediately and at least temporarily accept higher emissions? Will we try to extend the life of current nuclear reactors and shut them down afterwards while solving the shortcomings of renewables? Or will we invest in new nuclear technology to get new nuclear reactor types that are cheaper and safer? Or will we maybe do both? Opinion part starts here. Considering the risks that climate change poses for the biosphere and humanity, any technology that has a chance of contributing to a solution should be pursued. That's just good risk management and strategy. If preventing rapid climate change as quickly as possible is our goal, it might be a good idea to see nuclear and renewables not as opponents, but as partners. We know there's no time to waste, so we should keep all of our low-emission players on the field. As things are, both nuclear and renewables need innovation and investment. But if we don't know yet which technology will be ready how quickly, why not just invest in both and see what happens? And on the topic of current capacities, if we take nuclear energy offline right now, then that missing capacity will be replaced, at least partially, by fossil fuels. Even if new nuclear power plants in the West are expensive, in the long run it may be cheaper to build them as long as they prevent more fossil fuel capacity being added and paying for the consequences of rapid climate change. So, do we need nuclear energy? Well, it really depends how hard we choose to make things for ourselves. And in a world that's already having a really hard time quitting fossil fuels, why should we make things harder than necessary? Here in the Kurzgesagt labs, we test very important ideas to see what happens when you blow things up or play with black holes. Many of you suggested that we look into an idea that sounds reasonable: shooting nuclear waste into space. It's one of those concepts that seems like an easy fix for one of the main problems with nuclear energy. But it turns out this idea is not just bad, but horribly bad, and it gets worse the longer you think about it. Why is that? What is nuclear waste? Nuclear waste is a fuzzy term and comes in categories which vary from country to country. But in general, there are three broad levels. 90% is low-level nuclear waste, tools, gloves, or trash used at a nuclear facility that could be weakly contaminated with some short-lived radioactivity. This stuff is generally safe for normal disposal. 7% is intermediate-level nuclear waste, mostly materials that have been in close proximity to a reactor core long enough to become dangerously radioactive. With proper handling, it's either safely buried or melted down and mixed into glass or concrete and stored deep underground. So 97% of nuclear waste is similar to toxic byproducts from other industries. Not great, not terrible. We can handle it. The remaining 3% is where our problems begin. High-level nuclear waste is very concentrated spent fuel taken out of a reactor core. Formerly uranium, it's now made of various dangerous and often highly radioactive elements. As a bonus, it's also incredibly hot and not easy to handle at all. This is what we want to shoot into space. All in all, around 440 active nuclear reactors create about 11,000 tons of high-level nuclear waste each year. Since 1954, we've accumulated 400,000 tons of dangerous radioactive waste. Most countries are dealing with it by not dealing with it and kicking the can towards the future. Great, so let's launch it into space. According to scientists, space is big, and nobody lives there, so it seems perfect for yeeting away this mess. There are a few tiny problems though. Problem 1, stuff ain't cheap. Even though spaceflight is getting more affordable, it's still extremely expensive. Just to get something into low Earth orbit costs on average about $4,000 per kilogram. Putting that into perspective, it costs about $1,600 to mine, separate and fabricate 1 kilogram of nuclear fuel, so launching waste into space has suddenly made nuclear fuel for reactors way more expensive and greatly increased the cost of the electricity they produce. To launch 1 reactor's worth of nuclear waste would cost at least $100 million per year. To deal with all the 440 operational nuclear power plants' high-level nuclear waste would cost some $44 billion per year for space launch before packaging, transport and security costs are added. Okay, let's pretend we don't care. Currently, we couldn't shoot all the nuclear waste into space even if we wanted to. There just aren't enough rockets. In 2021, we saw a record 135 launches into space. If we repurposed each of those rockets and filled them all with nuclear waste, the total amount that could be lifted into a low Earth orbit, which is the closest orbit above the atmosphere, is nearly 800 tons. We'd need at least 14 times more rockets to handle just today's nuclear waste, let alone get rid of the hundreds of thousands of tons in temporary storage. We would need to create entire new space industries to keep up with the demand for giant, toxic space trash trucks. And it gets worse. Problem 2. Space is hard. We only made the calculation for low Earth orbit, where we send most of our rockets and satellites. Littering the space around Earth with thousands of casks of spent nuclear fuel would be a nightmare for space junk management and satellite collision avoidance. Worse still, at this altitude, there's still a little bit of atmosphere causing a tiny bit of drag, so we might have nuclear waste raining down from space within just a few years. Experts would call this a huge problem. Clearly, we have to launch our waste further. If we wanted to send it to, perhaps, the Moon, we either need way more rockets or we need to build much bigger ones, making it even more expensive. A single Saturn V, the rocket used by the Apollo program, which cost around $1.5 billion adjusted for inflation per launch, could get about 43.5 tons from the Earth to the Moon. So we'd need about 260 Saturn V rocket launches every year. And of course, using the Moon as target practice for nuclear waste-tipped rockets kind of makes a huge mess. So maybe don't aim for anything. Space is empty. Do we really need a target? Shooting waste in any random direction is, you guessed it, also a bad idea. Orbits are loops, which means they have a tendency to come back to where they started. Put enough in the sky in random directions, and you'll get one back eventually. So we'd want to launch our nuclear waste deep into space, which means we need even bigger rockets that would be even more expensive. Not that we would be completely safe then. Earth might run into these interplanetary caskets at some time in the far future and experience a pretty meteor shower made from radioactive dust. Okay, how about we shoot it into the Sun? Ironically, the Sun is pretty hard to hit. While the Sun has very strong gravity, everything on Earth is moving with respect to the Sun, including the rockets that we launch, meaning a rocket would have to cancel out all the orbital motion it has around the Sun so it can stop orbiting and fall in. Because of this, it's actually easier to launch a rocket entirely out of the solar system than it is to launch it into the Sun. But to do either of these things, we need even bigger rockets, probably the biggest we've ever built. Nothing works. The thing is, it gets even worse. Problem 3. Rockets go brrrr. Rocket engineering has taken huge steps since the Apollo era. We've made them relatively safe. We've mostly replaced the toxic explosive cancer fuels of the past decades with much saner mixes of liquid oxygen and hydrogen or kerosene. The newest designs even land themselves so that they can be reused. And yet, out of the 146 launches in 2021, there were 11 failures, which means that a sizable number of our rockets carrying high-level radioactive waste would be exploding on the launch pad, or in the worst case, disassembling at high altitude or crashing from hypersonic speeds. Each failure would be at least equivalent to a mini Chernobyl, but instead of being contained under a slab of concrete, spread throughout the atmosphere. Radioactive particles could make their way to faraway places by riding on the winds. Most would fall into the ocean, but some would land on the inhabited parts of the world. They could cover farmlands and get concentrated into our food or enter our water supply. Which is, well, bad. Imagine regular large-scale nuclear disasters happening. People wouldn't be happy. Conclusion and opinion part. Nuclear waste is scary, but the fear of it and horrible ideas like shooting it into space reveals how bad we are at understanding risk, because the largest amounts of radioactive elements like uranium and radon are actually released by coal. Burning millions of tons of coal each year leaves ash as a waste product that includes about 36,000 tons of radioactive materials. Less radioactive than high-level nuclear waste, but there's also a lot more of it, and it's handled way less carefully. Some of this ash is caught by filters, but most is simply pushed back into leaky mines, shoved into piles exposed to the wind, or poured into ponds that regularly spill into rivers and lakes. Living within 1.6 kilometers of an ash pile increases your cancer risk up to 2,000 times over the acceptable limit. And this is on top of other toxic chemicals like heavy metals and, of course, their massive CO2 emissions. And yet, while nuclear energy is flawed and its current form may only be a transitory technology, nuclear power plants are a harder sell than coal. Nuclear waste and the lack of willingness to deal with it are a real issue. It's not insurmountable, though. There are good methods to handle it, like burying it deep underground or reprocessing some of it into new fuel. But however we ultimately deal with this issue, we hope one thing is clear. Shooting nuclear waste into space is one of the worst ideas ever. Leaving Earth to find new homes in space is an old dream of humanity and will sooner or later be necessary for our survival. The planet that gets the most attention is Mars, a small, toxic, and energy-poor planet that just about seems good enough for a colony of depressed humans huddled in underground cities. But what if we think bigger? What if we take Venus, one of the most hostile and deadly places in the solar system, and turn it into a colony? Not by building lofty cloud cities, but by creating a proper second Earth. It might be easier than you think. Venus is by far the hottest planet in the solar system, with a surface temperature of 460 degrees Celsius, hot enough to melt lead. This heat is due to the most extreme greenhouse effect in the solar system. CO2 is great at trapping heat. Even a rise from 0.03% to 0.04% in Earth's atmosphere is heating up our planet right now. Venus's atmosphere is 97% CO2. Also, Venus's atmosphere is 93 times denser than Earth's. Standing on Venus's surface would feel like taking a dive about 900 meters deep into the ocean. The pressure would kill you instantly. It's a truly horrible place, so why should we even bother? First and foremost, Venus is almost as big as Earth and has 90% of its surface gravity. Surface gravity is a big problem when colonizing the solar system because it's very likely that long stays in low-gravity places will have negative health effects. Venus's size means it could be the second largest habitat in the solar system. A new home for billions of humans and trillions of animals, with oceans, lush forests, and a beautiful blue sky. A properly terraformed Venus may be the most pleasant place to live outside of Earth. While we can't exactly terraform Venus today, a slightly more ambitious future version of us could take this project on. It will take a few generations to complete and be a huge challenge like building the Great Pyramids was for our ancestors. But then, it's not like humans have never started projects that took more than a lifetime to complete. Okay, let's do it. Before anything else, we need to cool Venus down and remove the gas that makes up the extremely heavy atmosphere. As mentioned, there's a lot of it. Around 465 million billion tons. How do we do that? There are a few options. We could create giant solar collectors powering a huge array of laser beams that heat up the atmosphere so much that it's blasted into space. Although we would need thousands of times the entire power generating capacity of humanity, and it would still take thousands of years to remove the atmosphere. Another way is to sequester the atmosphere, binding the CO2 in different compounds through chemical reactions. We could mine elements like calcium or magnesium on Mercury and shoot them at Venus via mass driver systems, electric rails that make rockets unnecessary on smaller planets. The metals would combine to bind the CO2 into different carbonates basically forever. But the scale makes the whole thing impractical. We would need several 100 billion tons of material to sequester the CO2 this way. Seems like a waste of material and might take too long. An equally ridiculous idea that could actually work is to put Venus in the shade, literally, by constructing a huge mirror to blot out the sun to just freeze the atmosphere. The mirror doesn't need to be complex or massive, just a very thin foil with a little structural support. Building such a large flat surface so close to the sun will turn it effectively into a solar sail and push it out of position. So instead of one giant circular object, our mirror will consist of many different pieces. Annular slats of angled mirrors can reflect sunlight from one set of mirrors to the next. Mirrors would be angled, reflecting light from one to another until the light is redirected to the back, balancing the force on the front and holding them in position. After a few years of getting the infrastructure in place, things start slowly and then escalate. For the first few decades, the atmosphere slowly cools down but stays dense and deadly, until after some 60 years, it reaches the critical temperature of 31 degrees Celsius. Suddenly, the Great Flood begins on Venus as CO2 turns to liquid at this pressure and begins to rain down. A constant global rainstorm of unbelievable proportions lasting 30 years. The pressure and temperature suddenly begin to drop in unison. For almost a century, puddles turn into lakes and oceans. The surface temperature is now minus 56 degrees Celsius and the pressure has dropped to only 7 times the pressure on Earth. Finally, at a really unpleasant minus 81 degrees Celsius, the CO2 oceans begin to freeze and the rain turns into snow. This leaves us with a frozen Venus covered in oceans as hard as rock and gigantic CO2 glaciers. What remains of the atmosphere is mostly nitrogen at about 3 times Earth's surface pressure. If you don't mind freezing and suffocating, you can now take a stroll over Venus's surface. But the frozen CO2 remains a bit of a problem. At some point, we want to warm up the planet, but if we do, the CO2 ice will melt and fill up the atmosphere again. So we need some way to keep it from doing that. One is to simply cover it all with cheap plastic insulation and cover it up with ground-up Venus rock or water oceans. Although some planetary scientists will be very stressed out about us building a new planet containing a potential time bomb like that. A few unfortunately timed volcanoes could melt a lot of CO2 at once and ruin everything. Another obvious solution is to shoot it all out into space and collect it into a small moon for storage and future use. We can make this more efficient by using mass drivers instead of rockets, but moving all that mass will still be a pretty intense challenge that will take some time to solve. Whatever we end up doing with the atmosphere, to move forward we need water, which we could get from ice moons. Europa, a moon of Jupiter, has twice as much water as Earth's oceans. Now, catching a moon and transporting it through the solar system is not exactly easy. So instead, it might be easier to cut chunks of ice off Europa with an army of construction drones and shoot them at Venus using more of those mass drivers. Space tethers could save us a lot of effort and energy here. We made a whole video explaining how they work, but in a nutshell, they are slings that can take a payload on both ends. On Europa, they do most of the work needed to catapult our ice to Venus. The ice hits the Venus tethers, which gently drop it into the atmosphere, where it falls down as snow. In exchange, the Venus tethers get to catch CO2 ice shot up from below and accelerate it into orbit. We can remove excess nitrogen using this same method to further lower our atmospheric pressure. After a few decades or centuries, Venus would be covered by a nice, shallow, frozen ocean a few hundred meters deep. It would look extremely different from today. A few continents and countless islands have formed. This is beginning to look a bit like our planet. Now the last and most magnificent phase of terraforming begins, making the atmosphere breathable and adding life. First, we need light though, and we need to heat the planet up again. A Venus day is 2,802 hours long, more than 116 Earth days. So if we just remove our giant mirror, we would grill half of our planet. Even without the massive atmosphere, temperatures would reach unbearable levels. The simplest way to create a day-night cycle and let some energy in again is with another set of mirrors to illuminate our continents and melt our water oceans, which would let us completely control how much energy we get and where it goes. The atmosphere is now mostly made up of nitrogen and basically devoid of oxygen. So the first inhabitants will likely be trillions and trillions of cyanobacteria, which can get photosynthesizing and release oxygen. We know that they can quickly turn around the atmosphere of a planet because billions of years ago they were probably responsible for turning the toxic atmosphere of our young Earth into an atmosphere with enough oxygen for more complex animal life. But not only that, cyanobacteria can fix nitrogen from the atmosphere and turn it into nutrients that can be used by living beings. This way, they will essentially fertilize our dead ocean water and prepare it for more complex organisms. On land, our colonists need to grind down some of the former Venusian surface to make soil for nitrogen-fixing plants to grow on. Eventually, billions of trees would spread, creating large forests covering massive parts of the continents. Venus would turn green. To speed things up, CO2 would be strategically released to supply the plants and cyanobacteria. Areas already covered with plants could get extra daylight from our orbital mirrors, so the plants would be active for most of each day. Maybe we won't have to do this with the same plants and animals we know today. As genetic engineering matures and our understanding of genetics and the machinery of life expands, we might just engineer life as we need it. All in all, it would take several thousand years to make the atmosphere breathable by humans. In the meantime, you could stroll around with nothing more than regular clothes and an oxygen mask. Settlers would enjoy a vast new planet filled with resources and bathed in sunlight. They might think of new ways to use the vast amounts of carbon dioxide ice and nitrogen orbiting in space above. Industrial processes, rocket fuel, or even boosting the terraforming of another planet like tiny Mars. Venus is fully terraformed. Animals roam through vast ecosystems. Cities are being constructed. Billions of settlers and their descendants make this world their home. They will see images of the past, how Venus was once the most hostile planet around, how it took hundreds of years to freeze hell and to ship in the oceans, and another few thousand years to make it possible to breathe freely. They will barely be able to believe it. Okay, maybe it's not that easy to terraform Venus, and a lot of things must go right for this future to become reality. But it is possible, and with technology that is within the reach of a motivated and slightly more advanced humanity that wants to venture into space. The only thing that's stopping it is our imagination, and that at least is a problem that's easy to overcome. Today, we're doing something different. Our friend John Green will read a story from his podcast, The Anthropocene Reviewed. We hope you enjoy it, and we'll be back with a regular video soon.
So, if you've ever been or had a child, you will likely already be familiar with hand stencils. They were the first figurative art made by both our kids. Somewhere between the ages of 2 and 3, my children spread the fingers of one hand out across a piece of paper, and then, with the help of a parent, traced their 5 fingers. I remember my son's face as he lifted his hand and looked absolutely shocked to see the shape of his hand still on the paper, a semi-permanent record of himself. I am extremely happy that my children are no longer 3, and yet to look at their little hands from those early artworks is to be inundated with a strange, soul-splitting joy. Those pictures remind me that they are not just growing up, but also growing away from me, running toward their own lives. But of course, that's meaning I am applying to their hand stencils, and that complicated relationship between art and its viewers is never more fraught than when we are looking deeply into the past. In September of 1940, an 18-year-old mechanic named Marcel Ravidat was walking his dog Robot in the countryside of southwestern France when the dog disappeared down a hole. Robot eventually returned, but the next day, Ravidat went to the spot with 3 friends to explore the hole. And after quite a bit of digging, they discovered a cave with walls covered with paintings, including over 900 paintings of animals, horses, stags, bison, and also species that are now extinct, including a woolly rhinoceros. The paintings were astonishingly detailed and vivid, with red, yellow, and black paint made from pulverized mineral pigments that were usually blown through a narrow tube, possibly a hollowed bone, onto the walls of the cave. It would eventually be established that these artworks were at least 17,000 years old. Two of the boys who visited the cave that day were so profoundly moved by the art they saw that they camped outside the cave to protect it for over a year. After World War II, the French government took over protection of the site, and the cave was opened to the public in 1948. When Picasso saw the cave paintings on a visit that year, he reportedly said, "We have invented nothing." There are many mysteries at Lascaux. Why, for instance, are there no paintings of reindeer, which we know were the primary source of food for the Paleolithic humans who lived in that cave? Why were they so much more focused on painting animals than painting human forms? Why are certain areas of the cave filled with images, including pictures on the ceiling that required the building of scaffolding to create, while other areas have only a few paintings? And were the paintings spiritual? Here are our sacred animals? Or were they practical? Here is a guide to some of the animals that might kill you. Aside from the animals, there are nearly 1,000 abstract signs and shapes we cannot interpret, and also several negative hand stencils, as they are known by art historians. These are the paintings that most interest me. They were created by pressing one hand with fingers splayed against the wall of the cave, and then blowing pigment, leaving the area around the hand painted. Similar hand stencils have been found in caves around the world, from Indonesia to Spain to Australia to the Americas to Africa. We have found these memories of hands from 15 or 30 or even 40,000 years ago. These hand stencils remind us of how different life was in the distant past. Amputations, likely from frostbite, are common in Europe, and so you often see negative hand stencils with 3 or 4 fingers, and life was short and difficult. As many as a quarter of women died in childbirth. Around 50% of children died before the age of 5. But they also remind us that the humans of the past were as human as we are, their hands indistinguishable from ours. These communities hunted and gathered, and there were no large caloric surpluses, so every healthy person would have had to contribute to the acquisition of food and water, and yet somehow they still made time to create art, almost as if art isn't optional for humans. We see all kinds of hands stenciled on cave walls, children and adults, but almost always the fingers are spread, like my kids' hand stencils. I'm no Jungian, but it's fascinating and a little strange that so many Paleolithic humans who couldn't possibly have had any contact with each other created the same paintings the same way, paintings that we are still making. But then again, what the Lascaux art means to me is likely very different from what it meant to the people who made it. Some academics theorize that the hand stencils were part of hunting rituals. Then there's always the possibility that the hand was just a convenient model situated at the end of the wrist. To me, though, the hand stencils at Lascaux say, "I was here." They say, "You are not new." And because they are negative prints surrounded by red pigment, they also look to me like something out of a horror movie, like ghostly hands reaching up from some bloody background. They remind me that, as Alice Walker wrote, all history is current. The Lascaux cave has been closed to the public for many years now. Too many contemporary humans breathing inside of it led to the growth of mold and lichens, which has damaged some of the art. Just the act of looking at something can ruin it, I guess. But tourists can still visit an imitation cave called Lascaux 2, in which the artwork has been meticulously recreated. Humans making fake cave art to save real cave art may feel like peak Anthropocene behavior, but I have to confess that even though I am a jaded and cynical semi-professional reviewer of human activity, I actually find it overwhelmingly hopeful that 4 teenagers and a dog named Robot discovered a cave with 17,000-year-old handprints, that the cave was so overwhelmingly beautiful that 2 of those teenagers devoted themselves to its protection, and that when we humans became a danger to that cave's beauty, we agreed to stop going. Lascaux is there. You cannot visit. You can go to the fake cave we've built and see nearly identical hand stencils, but you will know this is not the thing itself, but a shadow of it. This is a handprint, but not a hand. This is a memory that you cannot return to. All of which makes the cave very much like the past it represents.